Morning, everybody. We're ready to get started. First talk is Reynold. He's going to talk about some advanced internals and performance tuning. The question is whether this material will be available afterwards, and absolutely. There'll be videos, all the materials, the slides, the exercises as well.
Is it walking mic? Or I guess I don't.
No. Sucks. Let me go see if I can get one.
Okay, thanks. Hi, everybody. Just give me a minute. So this is Reynold. I'm going to talk to you about the advanced Spark training. So unfortunately, the light's really blasting into my eyes and can't really have good eye contact with you. So it's not because I don't love you that I'm not looking at you. I'll probably be staring at my screens because of the setup. All of you have heard a lot about Apache Spark. Some of you might have even used Spark and prototype it, maybe even put something in production. And now what's next, right? Everybody can probably write word count at this point. So about this talk, I'm going to divide into 3 components. The first is I'm going to talk to you more about what an RDD really is, because I think that's probably the single biggest misconception people have about Spark. Even some of our partners in training sometimes talk about RDDs incorrectly. Does this work? Actually. And then I'll talk about how Spark actually executes programs, which turned it to a live Spark application. And then at the end, I'll talk about some tips in performance debugging, where how I myself actually go look at prompts when I have a Spark application performance prompts. So again, I'm assuming you sort of know the basics of Spark already. You can tell sort of what's an action and what's a transformation, and also you can write probably word count yourself in a couple minutes. If you can't do that, maybe there's the introductory material also going on in the other room. There's no shame in that. And the reason I want to tell you more about what exactly an RDD is and how sort of stuff executes is because of sort of this term coined by Jackie Stewart on mechanical simplicity, which is sort of a term that's having a growing traction, I think, right now in the performance world. Even though Spark is great, it's very simple. You can write very simple, concise programs. You can execute them distributably, sometimes very fast. But in order to write maybe the most performant programs, it's often good to actually understand the internals of how things work. It's like a good Formula 1 drivers would do. And sort of why am I, what's my qualification to talk about this? So I'm one of the core committers on Spark, probably work on every pieces of Spark. You've seen my small patches, big patches to the project. I've probably done a lot of performance studies on Spark, especially programs on top of it. And I sort of work on open source and product engineering at Databricks, and it's currently on leave for my PhD at Berkeley. So let's look at one very, very simple example applications, which really just having a new Spark context and then just run a filter. In this example, it's 2 RDDs. The first one's file, and the second one's errors. And then there's an action, which is a count, which is supposed to trigger some job. So now, as I started the presentation, I said RDD is probably the single most misconception to this concept in Spark, because a lot of people are drawn to Spark initially for memory computation. So what exactly is an RDD? Why don't you put up your hands if you think that's the correct answer? So A, RDD is just a distributed collection of data on disk. Anybody? Nobody. Second one, RDD is just a distributed collection of objects in memory. Couple hands. And the third, RDD is a distributed collection of objects in Cassandra, or maybe some. Anybody? Okay, so you guys are all wrong. The answer is really, an RDD can be any of the above. And let me explain what exactly I mean about that. A more scientific answer about what an RDD is exactly Actually, RDD is just an interface. So logically, it's a collection of records that's distributed. But how is it actually defined? So underlying in Spark, RDDs are defined as for the 5 primary interfaces. The first one is a set of partitions for an RDD. So this is given RDD, how many partitions of data do I have? And this is sometimes known as splits in Hadoop. The second one is list of dependencies, which is how a RDD depends on some of its parents. And you can view the parents as an input. And then the third is sort of a compute function, which given compute function takes in an input. The input itself is a partition object, and it's going to return an iterator that represents the data on this partition of data for this RDD. And then the fourth is sort of a partitioner, which indicates sort of what sort of partition scheme is this RDD using for a key value RDD. And the most common partition schemes are hashing and sort of range partitioning. By default, it's actually none, because you might just load a random data set from places that's no like specific partition schemes. And then the fifth one is also optional, which is the list of preferred locations for each of the partition. So the first 3 combined is actually defines the lineage information for an RDD, which means only with the 3 sort of functions that's defined for RDD, you could actually recompute an RDD. So if you remember sort of from your introductory Spark talk, there's a discussion about lineage and how Spark does fault tolerance by doing recomputation. So only the first 3 items combined can actually consist all the lineage information needed to recompute data for each specific partition. Because essentially, compute plus dependency tells you for each partition how do you compute them. And then set of partitions tells you how many partitions there are. And the fourth and the fifth, the partitioner and the preferred locations are actually used by Spark internally in the scheduler to optimize the job of execution. Essentially, the ultimate goal is to minimize any network I/O where needed. So it's a little bit dry. Let's give us some examples. So one example is HadoopRDD. This is a default RDD's return when you sort of create a text file. For example, Spark context.txt file. There's other sort of aliases for this function also. So for our HadoopRDD, the set of partitions is very simple. It's really just a set of splits or HDFS blocks on HDFS. Or some other Hadoop-compatible file system. And dependencies is none, because the HadoopRDD itself is sort of the beginning of, it's like a root of some tree. There's no, it doesn't have to go back anywhere else. It just points to stuff on HDFS. And then it's compute, essentially just giving a Hadoop input split or HDFS blocks, gonna read the data in and then return them in the form of an iterator. And our preferred location, essentially, it's the same thing as the preferred location of HDFS block. And partitioning is none, because for some random arbitrary data on HDFS, they most likely not partition according to like some hash scheme or sorting scheme. So another one's after in our sort of very simple example program, after running created the text file in HadoopRDD, we did a filter. So filter creates a new RDD, filter RDD. And it's also conceptually very simple. It's very similar. So filter itself, each of the partition in filter just maps to a partition in the upstream parent. Because parent is basically, there's a one-to-one sort of dependency, a way mapping from parent partition to the filter partition. And the dependency is what I just described, is sort of a one-to-one mapping between partitions. And then compute essentially just takes in the iterator from the parent, of the parent partition, and then runs a filter on it and returns a new iterator. And then last but not least, preferred location is for a filter RDD, it doesn't have any preferred location. So that doesn't mean Spark's not gonna schedule for any locality. It just means when there's no preferred locations defined, Spark is going to actually look at the parent's partition's preferred location, which in this case, if you have a filter RDD, you're running an action on it, Spark's going to actually schedule tasks using locality based on the filter RDD's parent, which in this case is a HadoopRDD. And partitioner, again, there's not really any partitioner information here. So from let's zoom out a little bit and look at sort of more 20,000 foot view of how this works actually in Spark. So essentially, there's two sorts of, I think, graphs, where the first one's might as well, it's more like a tree. So the first graph is the RDD graph, which is essentially just from a data set view. You have one HadoopRDD, and you have another arrow is just pointing down to be the filter RDD, where the HadoopRDD is the parent filter. But if you look at it more from, sorry, my screen's having some problem here. Same thing. The slides are only showing up half of my screen. I can't really see them from here. Okay, I'm gonna turn my head more around now. Sorry about it. I don't know what's going on. So this RDD graph, it's gonna be more challenging when I'm gonna do demos, where I have to type on one screen and start looking back at this. On the left, there's a data set view, which is it's very simple. It's a HadoopRDD pointing to sort of the filter RDD. It creates a very simple lineage. But the more if you zoom in a little bit and look at like the partition level view, this is exactly what happens, which is you have one-to-one dependencies between the partitions of the two RDDs. So essentially, you have arrows pointing this way. And when we actually run, I'm going to talk to you a little bit more about this in the execution part, life of a Spark application. When you actually run, so kick up a Spark job, what happens is for each of the partition, there will be sort of a task, which is a unit of execution running on those partitions. And keep running. So HadoopRDD and filterRDD are very simple, right? But often your data is probably more complicated than that, your data flow. And one of the very common operations is join. So let's talk about how the JoinedRDD works. So essentially for JoinedRDD, again, it's only 5 properties you need. Partitions, dependencies, compute, preferred location, and a partitioner. So for JoinedRDD, the partitions, essentially you give it a user-defined number of sort of reduced tasks. In this case, let's say, So in Spark, there's not exactly a difference between map and reduce, which I'll explain in a bit. But for now, I'm going to assume a lot of you come from maybe the map reduce, where you're sort of used to thinking in terms of map and reduces. So in the case of join, you have one sort of JoinedRDD, where you define, there's a user-defined number of partitions, which are used as in here referred to as reduced partitions to do the join. And the dependencies, you might have arbitrary number of sort of inputs from the parent, but for the sake of sanity, let's say there's only 2 of them. So it's like binary join operator. And then this essentially the dependency consists of 2 shuffle dependency on the parent. Which means you have to redistribute data, because the way you do distributed join on 2 sort of large data sets is you repartition the data according to the same partitioner, and when you get to a reduced side, you do the join there. So compute essentially just reads, once the data, so the data gets into compute, the parents are already sort of partitioned based on the partitioner we're specifying. Or based on the dependency we're specifying. In this case, the compute function only needs to read the data in from both parents. In this case, it's already pre-partitioned. And then we do the sort of the join, Cartesian join, or whatever join operator into use. And preferred location is really none, because you're doing sort of all-to-all sort of shuffle of the data. At the reduce side, there's not really any partitioning information you need. It's basically just, you can launch it on random node, and it's going to have the same effect. In the case of Spark, because everything we are using the hash partitioning to partition the 2 parent data sets, the partitioner of the JoinedRDD essentially just a hash partitioner that depends on the number of reduced tasks. So just to recap a little bit, I talk about 2 kinds of dependencies. It's really that's pretty much all the dependencies you need in Spark. So it's narrow and it's wide. In the case of narrow, it means 1-to-1, which is one parent partition can map to one child partition. And in this case, it's sort of when we talk about execution, what this really means is Spark can pipeline the two execution of two partitions. And on your right side, there's a Y dependency, which is a shuffle dependency. And the shuffle dependency, essentially, it's more like an all-to-all dependency where you have to repartition and redistribute the data from the parent when they get to the children to compute the children. So these are frequently used by sort of global aggregations or join operators, as we talked about just now, when the data are not pre-partitioned. So just to recap again, there's 5 properties of RDD. The first 3, partitions, dependencies, and compute, are sort of provide Spark with enough lineage information to recompute any of the RDDs. And the 4th and the 5th are the partitioner and preferred location, which gives Spark more information about how data are structured and sort of distributed, so Spark scheduler can optimize the program better to reduce the amount of I/O and the network I/O needed. Okay, now let's move on to sort of the life of a Spark application. Now you know what an RDD exactly is. It's really just an interface. There's many different implementations of RDDs. It could be RDDs pointing to Cassandra. It could be RDD pointing to like SAP HANA. It could be RDDs about files on HDFS. So how does Spark actually execute given a program? So in Spark, very different from sort of MapReduce, a Spark application is really just a JVM or a Python process that's running, and it's really running user code, whereas Spark is a third-party library that's running in the user code. And the central piece of this, which you all know, is Spark context. And what happens is when there's an action that happens, so essentially the Spark context is going to sort of get notified of the action, and it's going to start launching tasks, doing some scheduling and launch tasks. And the way that works is so in a typical Spark cluster, a Spark driver, which sometimes often called also a Spark master, and then this cluster manager typically, which in this case could be Yarn or Mesos or the Spark standalone cluster. And then sort of to your very right is the executors, which sometimes people call them slaves or workers. But the most precise term, according to the latest Spark release, is essentially you have your Spark application driver, which is really just your JVM program or a Python program, and then the cluster manager and the executors. Executors have a thread pool that's responsible for actually running tasks. So this is one difference, which some of the speakers earlier in the conference also highlighted. A big difference between Spark and Hadoop MapReduce is Spark actually runs jobs or tasks in threads in the thread pool on each of the executors, whereas Hadoop MapReduce just runs tasks in a higher way using processes. So there's a big difference here. That's one reason why sometimes when you port some Hadoop MapReduce program directly to Spark, you realize there's funny things happening, sometimes because of our concurrency problems, because some of the code you've written might not be thread safe in MapReduce. Like one sort of primary example is actually Hive itself. Hive, a lot of global static variables used to track arbitrary state. And when you actually run sort of directly, naively Hive code on Spark, you're going to run into a lot of problems where you might see like random null pointer exceptions. This is one big difference here. And then the truth is a single application can usually run multiple actions, and each action will kick off like one Spark job. So how does that run? How do we actually run jobs? So given a let's say I have a very simple program. Here's RDD1 join RDD2 and doing group by and filter, and then just finally doing a count, where it's count as an action. So essentially, when you're creating all these RDDs, if you actually look into the implementation of these functions, what they do is really just creating a new RDD and defining the dependencies, partitions, compute function, preferred locations, and all of that. It's actually very simple. I encourage you to actually go look at the Spark source code. One good place to start is the rdd.scala class. You can look at how exactly the things are implemented. Each of them is probably less than like 10 lines long. It's very simple. So each of the RDD object, just pointing to some parents, it actually consists of a whole graph of how you can recompute this RDD, along with like the actual partitioning and data distribution information you can use to optimize the program. And then when you run an action, what happens is the underlying Spark scheduler, which in this case is called DAG Scheduler. And what happens is the RDD graph itself, again, this is on your very left. This is just the top level graph from a data set RDD point of view. But the internal is represented by sort of tasks. What happened is you send the RDD graph to the scheduler. The scheduler is actually going to split the graph into multiple stages. And each stage, the way you define stage boundaries, data operations you cannot pipeline anymore, which in this case really means a shuffle dependency. So you're given a stage, you're given a tree sort of, or a DAG of tasks, you're gonna cut them into sort of multiple stages, using the shuffle dependency. And then the DAG scheduler, so technically it's some other underlying scheduler also, but so from a higher level point of view, the DAG scheduler essentially breaks them and then submits the stages of tasks into the executors for execution. In this case, in a thread pool. And then when the executors finish executing them, it's going to either return the data to the driver or prepare the data for sort of shuffle operation. So a DAG scheduler essentially takes in sort of RDDs and, or it's more specific, takes in a single RDD and a set of partitions it needs to compute. This is actually what happens when you actually run an action like count. Essentially what it does is triggers it submits to the scheduler a job, and this job consists of sort of the RDD you're counting and a function or a set of partitions you want to do on this RDD. And in this case, it's just like computing the number of sort of times each, computing the number of elements in each partition. And the output is essentially the output of the actions. In the case of count, it's just a long on every partition. And then finally, the task scheduler is gonna, or the executor is gonna send back the count for each partition. The driver is responsible for aggregating all of them in the count function itself. So the DAG scheduler does actually quite a bit of stuff. So I talked to you about it's gonna build stages of a task based on some input RDD graph, and it's gonna break the graph down into stages of tasks based on shuffle dependencies. And it's gonna submit them into a low level implementation of the scheduler, which right now is like meso support, yarn support, and standalone support. All of this sort of, it's designed in a way internally in a very pluggable, so you can actually plug in newer scheduler or newer cluster managers as you wish. But essentially, DAG scheduler breaks stuff down into tasks and sends a task essentially to the lower level scheduler, and the lower level scheduler dispatch them to the cluster for executors to execute based on locality information is passed in. And what happens if stuff fails? So this is the part about fault tolerance. So and then the cluster computing stuff get fail. The DAG scheduler itself is actually responsible to resubmitting stuff that fails. So for example, if one of the stage failed, the DAG scheduler is going to actually reschedule the stage or some of the tasks in the stage into a different node for execution. This is how the fault tolerance is achieved. The DAG scheduler itself knows about all the lineage information that's passed in from the user level program. And using that, you can sort of recompute arbitrary programs as they want. So I mentioned to you earlier about like pipelining and all of this and this partitioning. So the DAG scheduler itself also employs a number of techniques. One example is sort of pipelining. So when you have one-to-one dependencies, which means sort of a task only depends on its parent, or a partition of RDD only depends on the one partition of its parent. In this case, there's no difference to break the thing down into different stages. You could actually pipeline and collapse them into a single stage. So one example here is, does that work? Yeah. Does this one work? Okay. So one example is sort of I've drawn sort of a partitioning graph to your right here. It's a fairly complicated example. It's like you've probably seen this example before also. You're doing group by and you're doing sort of union of two RDDs and you're joining them together. In this case, Because if you look at it, C, D, and F, these three partitions, you could actually, it's all one-to-one dependency, which means you could really have a single task that executes all three. So in this case, Spark's actually going to like collapse them and just do them with a single task. And same for like this one, and for this one, and for this one. And then once you get to here, so there's a join operator now, what happens is Spark needs to pick sort of a join algorithm based on the partitioning itself. So if you look at the stage A and stage B here, this is a group by. Group by means you have to sort of, you need global data to group the group by, which means eventually on each of the sort of partitions in B, all the data with the same key needs to be end up on the same partition. So this is also a shuffle. In the case of a shuffle, you can't pipeline it, which is why there's two stages here, A and B. But if Spark Scheduler look at this graph, it's going to realize, oops, B is already hash partition, depending on whatever you use for group by, but most likely B is hash partition into like 3 different partitions. Whereas F is, doesn't really have a partitioner because there's some random input data that's coming in from this or some other file system. And when you run a join, if the user desires a join level, so using 3 reduced tasks to do the join, it means the join itself is going to have the same partitioner, same hash partitioner as this, the group by result of B. In this case, the DAG scheduler is going to figure out, oh, it's actually pretty simple. We don't need to do an extra shuffle between B and, this is the part I don't see on my screen. B and G. There's no need to do a shuffle on B and G. So between B and G, it actually becomes a one-to-one dependency instead of a shuffle dependency. So you avoided the whole extra shuffle here. But because here we need to repartition data from 4 partitions into 3 partitions, there's actually a shuffle dependency on this side. So essentially to do this join and do this whole thing in 3 stages, there's the first stage, the CDEF, which is essentially just like all pipelinable, and then you trigger a shuffle after that. And then the stage A, which triggers a shuffle to do the group by. And then you compute the final G, which is essentially by joining B and F, where B doesn't need to be shuffled and F needs to be shuffled. So this is with all the partitioning information we are getting from sort of the RDDs, this is how the DAG scheduler can actually optimize and reduce network I/O. Because if otherwise, the naive way of running this program is you run one stage of task, which is just running C, you're reading C from data. I mean, think of it how you write it in MapReduce, which is you have one map program that reads C from disk. You have another map program that reads E from disk. And then you have another MapReduce program that reads D from the output of C, which is most likely some temporary file now on HDFS. And you run to F, and just keep going. And this, if you run this naively in MapReduce, you ended up actually doing 2 shuffles, or doing 3 shuffles instead of 2. So one is the first A to B, and then B to G, and then F to G, all 3 shuffles if you run it naively in MapReduce. Whereas in Spark, you pipeline a bunch of them, remove a bunch of the extra jobs you need to run, and you also so reduce some shuffling you need to do. And the scheduler is also smart in the way that they will try to reuse sort of in-memory data as much as possible. So for example, if we have marked, you probably all know about this, but if we mark B as cached or persisted in memory in Spark, when you actually run this program, Spark is going to go all the way only back to B instead of going all the way back to A. In this case, even it avoids reading A from this, as well as avoids a whole round of shuffle. And tasks. So tasks are sort of unit of work to be executed on a cluster, on an executor in a thread. So technically unlike Hadoop MapReduce, there's no sort of separation of reduced tasks and map tasks. There's really only tasks. It's a single sort of conceptual unit, and any task can, under the hood, any task can do arbitrary things, but usually ends up with having only a sort of
two outcomes. One is it's going to execute some stuff and it's going to send the result back to the driver, which in the case of a count, this is what happens. You just send a count back to the driver. And the other one is a task, it's what we call a shuffle map task. You don't really have to remember the name, but it's just to tell you a little bit of how stuff works under the hood. The other way is shuffle map task, which essentially will repartition, we'll partition the output of the task into mini blocks for shuffling. So the shuffle operation is essentially what we use to redistribute data from partitions to partitions, from the parent to children. The way it works is it depends on, it's an all-to-all communication pattern, and then the way it works is the user defines a partitioner. So I make a tiny mistake here. It's not just hash, but the user defines a partitioner, and the partitioner is going to tell essentially one function, which is the get partition, which returns like the number of partition index based on the input. So for each of the input, we're going to run it through a partition, and a partition is going to redirect which bucket this input should go to. And then on the reduce side, the reduce tasks are going to actually fetch the tiny buckets, which are shown in more detail in the next slide. So there's a lot of, if you remember just a couple slides ago, we're talking about DAG Scheduler and optimizations. So shuffles are, again, just avoided when possible by the scheduler. If the scheduler knows data is already partitioned in specific formats, it doesn't actually have to run any of the shuffling. For example, if you know your data set's already hash partitioned by key, then when you're doing aggregation on the key, you actually don't need to partition the data, or don't need to shuffle anymore. So for those of you, how many of you went to Aaron's talk? I'm just curious. Can you put up your hand? Aaron Davidson's talk on Spark internals. It's probably, yeah, I guess. That guy was a beard. All right, okay. So you've seen this picture. For those of you who have gone to his talk, you've seen this picture before. So exactly, when I show you the graph here, it looks like as if whenever you start shuffling data, we actually push the data directly to a reduce side. But that's not exactly what's happening. What happens is on the map side, we partition each of the block, or each of the partition, and then we, based on the partition, we're going to separate them into like tiny buckets. And then we write these buckets to disk, which for small and medium-sized shuffles, most likely the buckets actually fit in the OS buffer cache. But for very large files, they actually get flushed to disk. And what happens is we're going to do this for every single one of them. When we start the reduce task is going to start fetching the data. So essentially, the first reduce task is going to fetch the first bucket from every single map task. And so on for the second one, it's going to fetch a second bucket from everyone. This is how you do all-to-all of data shuffling. So hopefully, with this flow, it explains a little bit about how Spark actually works. The way it works is we have this graph of RDDs, and we pass it into a scheduler. The scheduler breaks it down into like stages of tasks, and essentially we send the task to the executors for execution in threads. And then we get results back, or we get like shuffle outputs on disk. So the last part of this talk is going to be a combination of a lot of demos and just some tips on performance debugging. So now you understand how Spark works. You have jobs that get broken down into stages, and a stage consists of tasks that are being executed on executors. And your Spark programs may be running slow. Right? This is sort of a very common, maybe a common problem. And what do you do? So I sort of categorize performance problems into two categories. The part about distributed performance, which is how is data distributed, how are the tasks distributed, and this is the specific problems more introduced by just a distributed system. And then there's the second part, which is local performance, which is if you run the same algorithm still on the local node, maybe you could run into some of the same programs too. Like for example, you could certainly write a local program that's also very slow. So I'll walk you through some of the steps like I myself usually use and follow when I run into performance problem and how I debug them. So two of the most useful tools you can have. It's actually the application web UI, which by default goes to port 4040. If you've never used it, you should. And the other one is probably slightly less exposed. It's the executor logs, which by default goes into the work folder in the Spark, on each of the Spark executor or worker nodes. And this is where all the the task information are logged. So when you run into sort of a slow Spark application or a slow Spark job, the first step is, assuming you have a live web UI, the first step is usually look at the web UI to find the stages that are slow. Because remember, you have Spark jobs that get broken down into stages. If you can isolate and find the stages that are slow, that's usually the first step towards debugging this. So the web UI itself, how many of you have never used the web UI? Or maybe people who have used the web UI, put up your hands. OK, say probably like 80%. So I'll show you the web UI in a minute, a live one. This is just a screenshot of it. Essentially, this is the stages page, which just shows the history of stages that are being executed. And shows like how many tasks are being executed right now and how many of them are done, what stages have completely completed, and what stages have completely failed. It's very useful for debugging. And this UI is going to get better in the future version of Spark, where we actually have the concept of jobs directly built into this UI. So run an action, you don't see a bunch of stages. You actually see a job, and then going to the job, you can see stages. If any of you was interested in working on that, let me know. So often, when a stage is slow, the first thing you want to identify is, am I seeing stragglers? Which in this case just means some of the tasks are running slower than the others. And this is pretty easy to tell usually. So when you go into, when you click into the stages, again, I'll walk through them later, but right now just showing on screenshots. If you click into the stages, you lead into like a stage detail information page where there's actually some summary metrics for tasks. So I ran like a very simple job yesterday. This is essentially what, so I triggered like kick off one job yesterday. This is what happened. The job contains, I think, 19 tasks. If you look at it, it actually shows you a distribution of the tasks. Like for example, what's the minimum amount time it takes for one of the 19 tasks to finish? What's the 50 percentile, the medium? And what's the max? Usually when there's stragglers, you will see the max being far, far bigger than the median. This is when you can identify stragglers. Once you identify stragglers, there's typically two causes of stragglers. One is it's a distributed system. Maybe one of your node is just slow. Right?
Do we expect all the partitions to be the same size?
No, that's my second part. The question was, do we expect all the partitions to be the same size? You can't expect that because, again, RDD is just like a specific, it's just an interface. So depending on the implementation of RDDs, you might end up with partitions of different size. If you have like a HadoopRDD, which points to like blocks on HDFS, the blocks are all of the same size. But you can't guarantee that, for example, once you do a filtering. So sometimes it's because of like slow nodes. Maybe some node is just running slow. So I have a very simple program here. What it does is it creates RDD with 15 elements. And for each of the element, I partition it 15 ways, which means each partition contains only one element. And then I'm going to do a map, which means for each of the partition, have one element really, only the index, and I'm going to get the host name of that. I'm going to compare the host name. If it's equals to one of the executor, I'm going to sleep for 10 seconds. Otherwise, I sleep for 1 second, which this is just a very simple program to sort of simulate a very slow node. So let's try, and then I run a count, which is counting, basically running a task on each of the partition. And I'm going to try run this if I got internet. So I've started sort of a Spark cluster with a Spark shell open right here. Let me check. The guys in the back can see this? Good. Show this one there. Okay, so it's very big, but there's a Scala shell, the Spark shell here, which is what you expect. So you could run like the most stupid program of 1 to 10 and then counting how many times whatever stuff happens. It's going to run, it's going to return 10, like 0.60 milliseconds. So let's try and run the program I just designed. I'm just going to paste it in instead of typing in. So what happens is if you go to the web UI, you're going to see 11 of the 15 tasks finished very quickly, because each of them is only supposed to take a second. And then the last 4, it's kind of slow. And finally finished, it's supposed to take 10 seconds. So it took exactly about 10 seconds for the last 4 to finish. And the reasons, I actually have 3 executors here. So it's a driver and 3 executors. And essentially I have 15 elements, each of them supposed to run 5 of them, actually. So if you go into the web UI, for the detailed information for stages, now you see actually the medium range for the task, it takes about only 1 second here. Whereas the maximum time is 10. This is kind of suspicious when you're debugging a program. Like, why is the max be so far off from the medium? Now, if you look at the aggregated metrics by executor, this is another different view of seeing this UI. Essentially what it does is just, this one aggregates everything for all tasks, and this one aggregates stuff grouping by the executor ID. And you can see the task time here is 40, whereas on every other executor, it takes like 5 or 6 seconds. So what happened is one of the 6 elements that get scheduled to the executor 0, 6 tasks that got scheduled to the first executor, whereas that 4 of them ends up on the last one, each of them taking 10 seconds. So it takes like 40 seconds in total. This is the aggregated time. This is not like wartime. It's happening. If you scroll down to like tasks, you can see the duration of each task. You can even sort them by duration. You can find, oh, there's 4 of them is really slow, and they're all on the same node. And now there are still different possibilities of stuff happening. Maybe this node is just really slow. Maybe there's some contention. Maybe there are other stuff running on this node that's taking the resource away from Spark to finish. So what can we do here? This is actually a very simple way of solving usually problems related to sort of stragglers from a slow node. What you do is you turn task speculation on. So speculation, for those of you coming from MapReduce, you're probably familiar with the concept. Essentially what happens is Spark's going to look at, once you turn speculation on, Spark's going to look at the distribution of tasks within each stage. It's going to assume tasks within stages are sort of somewhat uniformly distributed. It might have variance, but it's somewhat uniformly distributed. If one task is much, much slower than another, it probably means as a straggler, we can try relaunch the task onto a different node and let them race to see who finishes it first. And usually, when you have a slow node, when you turn speculation on, it's, that fixes the problem. So let's see how we do it. The way you do it is, so let's just shut down Spark here. In the, you could set it programmably in Spark when you start the program, but you could also just edit the default configuration, which is just a conf Spark default. And I'm just gonna, it's going to add a line to it that says Spark speculation space true. So this just set speculation to true. You can find, by the way, you can find a list of all the config options directly on the Spark documentation website. So once you do this, let's just launch Spark again. Screen is following me. So this time, let's run the same program. And now let's go to the web UI. So you see, it finished in 3 seconds instead of 15 or 10. And the reason is, if you're going to count, now this time, instead of launching 15 tasks, Spark actually launched 19 of them. And the reason is, once you go here, so if you look at task 2, you're going to realize there's 2 of them, task index 2 and 2. And the first copy took 10 seconds. The second copy took only 1 second. Essentially what happened is once enough tasks are finished, Spark knows the distribution of how fast the tasks run within each stage. And when speculation is turned on, when Spark realized this thing's been running maybe for like 3 or 4 seconds, it hasn't really finished yet. The other tasks all finished within a second. Maybe I can try relaunching this on a different node. So if you look at this, it's actually on 223 instead of 222. So launch this, and on a different node, that node is no longer slow. If you remember our program, we only used to pinpoint one of the node and sleep for 10 seconds. The other nodes don't do that, so now it's finished in a second. So overall, the whole thing finished. I mean, it's not a second, but then it's much better than waiting for 10 seconds. Overall, it finished in 3 seconds. Yeah.
If a job has many stages, Spark figures out there's a straggler. Will Spark remember the next stage?
It doesn't reuse straggler information across stages. I mean, part of it is stragglers is not always a reliable way of determining like a machine is slow. But this is certainly one aspect of things that can be improved like in the future, which is if historically it's always slow, maybe we can just avoid that. What we have added is historically if a node fails all the time, we exclude it. But we haven't added the one about like the slowness yet. That's, I think it's a pretty cool idea that we can experiment. So another kind of straggler is just data skew. Yeah.
The drawback to enable this thing is the job will be submitted, the job or this task will be submitted over and over, so I can use more resource from my input.
Yeah, exactly. So yeah, the question is a very good question. The question is is a drawback of here with turning on straggler. Or turning on speculation because we might be launching more tasks than we need it for the bare minimum. Yes. Although for the second sort of copy of tasks, they usually finish much faster. So overall, I mean, you are using more resources. If your cluster is running at 100% capacity, this is probably not the things that's going to help you much. But often clusters don't run at 100% capacity. Yeah. Another common problem of the straggler is really just data skew or some sort of computation skew specific to partitions. It's not because of like hardware resource running slow. So one very simple example is I'm just going to, again, have 15 partitions. Each partition have only one element. And what it does is it does a flat map, which means it's going to expand the element into multiple elements. In this case, for each of the element is starting from 1. For number 1, I'm going to generate one number, which is 1. For number 2, I'm going to generate 1 to 2. And for number 15, it's going to have 15 of them. And then for each of the output from the flat map, I'm just going to sleep for a second. So in this case, what's going to happen is on the first partition, you only have one element. So the first partition is going to finish in, try run this actually. Let me turn speculation off first. Oops, actually, this program's not going to run the way I write it. Shell thinks everything's on a different line. Okay, so I've launched the task. There's 15 of them again. This time it's just going to continue running. And if you go into it, you're going to see the first task takes like 1 second. The second task takes 2 seconds to finish. The third takes 3 seconds, 4, 5, 6. Eventually goes to like 15. So The problem with this one, the problem with this program is even if you turn speculation on, it's not going to really help you because speculation just launches an identical copy of the task somewhere else. Like this is in this case, the thing is more inherent to the design of the algorithms I'm running. Like if I really just want to run this specific thing, which is a very stupid program, just sleeps for like 1 to 15 seconds, there's no way to get around it. So, and this is actually very easy to tell, right? If you sort of look at this task detail page, the stage detail page, you see the breakdown of execution time. You can even sort the tasks by time. You can find out what tasks are running slow. And speculation is not going to help you here. What usually happens here is you really rethink how you're going to redesign the algorithm. Sometimes it might be because of data. Like for example, just one partition happened to have a lot of data. In that case, you might want to split your partition into multiple partitions. And now, let's say you sort of figure out it's not exactly like Straggle or maybe like all your tasks are sort of running slow. And you can't figure out why. You think it probably should run a lot faster. There's usually 2 common causes for that. The first one is garbage collection. It's running on the JVM. You relies on garbage collection policies to actually clean up the dirt. And the second one is just maybe the performance of the code running on each of the tasks is kind of slow. So for GC, it's actually not, it's pretty easy to identify GC prompts usually. For tasks that are already finished and you feel it's like finished slower than you would like, what happened is you could easily look at, I haven't triggered GC yet, but let's see. No, but I have one slide for that actually. But let me just try to force a GC. Can't find it. Here we go. Let's hope I succeeded. Yes, OK. So I just ran a program that creates a lot of garbage. And so when you go into the sort of detail page of Spark stages, and at the task level, you could actually see the GC time for each of the tasks. So if you sort the thing by GC time, you're going to see the 79 milliseconds of the 3 seconds when executing this task 1 is just spent in GC. So this is not a big deal because 79 milliseconds is only a small fraction of the 3 seconds. But sometimes you might find like maybe the duration is like 20 seconds, but the GC time is 19 seconds. That probably means you're sort of in trouble. And there's a lot of memory pressure in the system. But another problem is this is for tasks that are already finished. What about like tasks that are running? Like maybe one of my tasks is really not sort of completing because it's really, really slow. And you want to see if GC is the problem. And it's not showing up on the UI yet because there's no progress reporting. So one way to do it is look at the log from the executor, which is sort of your second best friend after the web UI. So here, what I have here is, I have a SSH into one of the host nodes. One of the executors is like 222. And so this is a Spark folder. You probably are familiar with this. And there's a work folder here. If you look at this, usually the way I do it is just ls lthr, which is going to show me the list of this really big font. It's going to show me the list of like folders based on the creation time. So the last one shows up last. Usually your application that's running is the last one, unless you're racing with your colleague, and it might not be the last, but it's usually the last one. And then you can go into this folder and look. If you do ls, it's like only a number 2. What that 2 means is an executor ID. So essentially, like host 222 is the executor number 2. If we go to the web UI, we can verify that. Here, executor number 2 is 222. So once you're in here, this going to 2. And the 2 files. Sometimes there's more. Like if you do add jar, the jars get added here also. So it's standard out and standard error. If you look at standard error, this is all the log4j log. for this executor. So for example, it's going to say sending result for like task 25 back to the driver. It's going to say like finish the task 25, and it's going to say like, for example, start task 25 at some point also. Or not start. Or running task ID 14 of this. Whereas on the standard out part, you see some GC log. And this is just typical GC log coming from a JVM. For tasks that are running, essentially you can come here and look at, for example, how many seconds have we spent running GC for the past while. And this is not by default logged, because this is just a JVM option you can turn on the executors. The way you turn it on is, if you set a Spark option, this is what you need to do, the actual jobs. So you all get the slides, so you're doing to like take notes and write this down. It's kind of painful to write the options down. If you set the actual job options to include like information to tell the JVM to actually print the GC log, you will see them in a standard output on the executors. So I've done that. So once when you have like GC prompts, you realize maybe GC problem allocating too many objects. It's usually good to find out like what the hell you're allocating. And this is like very standard JVM tool like jmap. This is sort of your best friend. You can just look at the, you can actually use jmap to get a dump of the heap to analyze how many objects are like, how many instances of each object you're allocating. So let's go do an example. So let's start the Spark shell again. In this case, I am just going to, if you remember, I ran a thing that created a bunch of garbage. I'm just going to rerun that. So in this case, I define a dummy object. Or it's more like dummy, what the? Yeah. I'm going to define a dummy object, and I'm going to just create like 100 million of them. I think it was 100 million, yeah. Maybe even more. And it's going to, actually pretty quick. So I'm going to go to one of the worker. So LTHR is going to find me the last one. Actually, sorry, I'm not looking at. So if we look at 2 now, we should see some GC information. Yeah, some GC happening. And if you do a JPS on the worker, you can find all the Java processes that are running. And usually the Spark executor comes with the name like core screen executor backend. If you remember the PID, you can do a jmap and histo, the PID. I'm just going to pipe it to less. So this way, I'm going to get a heap dump. It's going to take a while. It's probably need to make this smaller. Yeah, so this actually tells us how many instances of different stuff are being allocated. And for example, we have almost 1 million of, or 10 million integers and 10 million dummy objects. And then this is like the amount of size they are kept, and it's like a giant integer array. I think that's, I actually have no idea why that showed up. So one difference is jmap histo actually give you just a, a dump of the heap. It doesn't tell you what's exactly that no longer needed. If you add, oh man, this screen is screwed up. Okay. If you just add a column live, it's going to actually force the executor to do a GC, which clears out all the temporary objects. And then it shows you the histogram. So if you remember, the way we created a garbage program is that we created a lot of dummy objects, but we no longer keep reference to them. So they're technically dead objects that's not reachable in the heap. If you do histo, they're going to show up until the next GC. But if you do histo live, they're going to remove all of those, and the output you see doesn't no longer contains the dummy objects. So jmap is a great way of sort of helping you find out what objects you're allocating. And usually this and you can use that information to help debug your application program. So just giving one tip here. So Sometimes it's hard to do because you probably don't care about hyper-optimizing your program, but the best JVM program, sometimes you resort to doing zero allocation. So one way of doing that, you might think it's really hard to do that in functional programming, but one way of doing that is instead of using maps in Spark, which triggers a closure per a row, you could use a map partition. Whereas a map partition essentially runs a whole partition of data in a single task. So in this case, if you rewrite the map into a map partition, you could actually get a handle and allocate a dummy object per partition, and then reuse that object in each of the map. So it's not always worth it to do it like this, but sometimes you're looking for ways of hyper-optimizing your program. This is one of the ways you could do it. Leverage map partitions. So the last part of it is just local performance. Like what if just some random stuff running slow? This is very similar to probably like how you would debug a local JVM program. Again, each Spark executor just runs as a JVM or processes. There's a million other tools you could use for debugging, profiling. So one of my favorite is really very simple, just JStack. And here I have a very simple program. Essentially, I have two functions, which is, the first one's a cheap function, which just returns, and it takes an integer, returns a +1 for the integer. The second one's the expensive function, which sleep for a second. And then I'm going to run 100,000 of this cheap and expensive computation. I'm going to save the data out to HDFS. So let's try just doing that. So I'm just going to define the cheap function and the expensive function. And then I'm going to run, just going to save this and run it. So now, if you go to the web UI, you're running this program, I realize, like, wait a minute, I'm just like doing 100,000 stuff, counting them, maybe incrementing them by one. Why is it really slow? And have no like task reporting. It's just running, but I don't know why. What the hell's going on? So this time, you could again just you could go to one of the executors. So I'm going to SSH into one of the executor. And if you do a JPS again, you're going to see the core screen executor backend. So if you just do JStack, which gives you actually stack dump of their program, if you pipe it to less, usually the first thing I do, there's a lot of threads happening. You don't exactly, it's hard to find out which one's which. You don't have to scroll through them. Just search for Spark. Usually when you search for Spark, you're going to find a program that's like this thread that's actually running for Spark stuff. You're going to see the whole stack trace of it. And you see right now we are at some expensive computation here. And if you do JStack again, very likely you ended up being in the the slow code path, which is again some expensive computation. So if you do it again, it's going to probably happen again, just some expensive computation in the stack trace. So a very ghetto and simple way of doing performance debugging is really just running JStack a couple times on the executor to see what happens. You can even create like a dump of the stack trace and do a binary, like do a diff of the stacks between 3 different snapshots and see what happens. And then usually you can find out the problem very quickly. If not, there's other tools, like for example, YourKit's a great one I often love to use. It gives you a very nice breakdown of things, but often, like I think 90% of the time for low-hanging fruits, a simple couple JStacks are good enough. But otherwise, there's expensive commercial tools out there like YourKit, or you could, it's free for open source development and stuff. So, very last one, which is just what if my program's running fine but it's not returning the correct data? So again, just one thing to remember, Spark programs, unlike Hadoop MapReduce, it really runs in the usual level JVM process. It's very easy to debug. You can even use the JVM debugger or run it in the IDE, like IntelliJ or Eclipse, to step through the programs one by one. It's easier if you run it in the local mode. And in this case, you could probably grab a sample data set. It might be slightly harder on a cluster mode, but it's still, often you can probably just run your program locally with sort of a sample data set, maybe with a couple different blocks of the data you have. Or you can run in a cluster mode, and you can still do step-by-step breakpoint debugging. It just won't be able to break into the executors. So this wraps up my sort of very long presentation. Just to sort of summarize what we have learned. We learned about exactly what an RDD is. So hopefully, like starting from now, fewer and fewer people is going to say, so Spark only works for in-memory data. RDD means the data is in memory. RDD doesn't exactly mean the data is in memory. It's only when you cache the RDD, the data is in memory. And we learned how sort of Spark executes sort of schedules tasks, and I'll just walk you through some of the basic performance debugging I myself have done. So this is the very first time I've given this talk, as a lot of the materials were new, so there's certainly rough edges. So I would love to hear feedback. But I think because I'm running out of time, we're gonna go to the next presentation soon, but you feel free to like talk to any of us about like any of the things in Spark. Thank you.
Hey. I don't know, actually. A bunch of people left. Let's say like in like 5 minutes or so. Okay, so I'm gonna give just 5 minutes for people to like grab drinks and things, and then I'm gonna get started. Oh, it's good? Okay, excellent. I'm redoing all the permissions again, but I think that will be fine. Yeah, because it does like, it makes an HTTP request for each one. I don't know, this is the stupid side of it applying. Maybe there's like a better way to do it.
Just get that. Bigger the better. Okay. There you go.
And what mic should I use?
Good. Yeah, I know it's standard, but is it bigger? Bigger. Thank you. We do have this.
Okay.
We have the podium mic as well if you want to stay stationary.
Or use
I'll
this.
turn this on
Okay.
just in case.
Cool. Okay, so on to the second talk of the morning. I'm here to talk about Spark SQL and kind of how it's going to allow you to access data in a unified manner. This can be fairly interactive, so feel free to raise your hand if you have any questions. It's kind of hard to see with the lights, so scream out if I'm not seeing you. But here we go. So Spark SQL. First of all, what is it? What are the pieces? What makes it up? So kind of at a high level, when we started building Spark SQL, the first thing we did was we built this layer called the Catalyst Optimizer. Basically what this is a mathematical language for representing data flows. So think things like projections, filters, joins, aggregations. But at this layer, it's completely Spark agnostic. And what we're actually doing is basically we take your SQL commands and we compile them down to this mathematical representation. And the nice thing here is then Catalyst can actually do quite a bit of optimization, rearranging the data flow to execute more quickly. So if you have like a where clause in your SQL statement, for example, one of the tricks that we can do is we can actually push that down deeper so we can filter earlier and do less work. We can also eliminate all the columns you're not going to use, kind of things like that to eliminate the amount of network activity that needs to occur. And so that's kind of the top part. It's something that you won't interact with directly as a user, but it's kind of good to know that it exists. And then on top of that, we built the Spark SQL core. And so here's where we actually take these mathematical representations of your data flow and compile them down into RDD graphs. And so basically, every operation in Spark SQL is just doing the same RDD operations as when you write your own Spark programs. It's figuring out the correct order and actually doing a bunch of tricks under the covers to make sure that those queries then run as quickly as possible. And then the other kind of part of Spark SQL core is the ability to read in different data formats. So I'll talk a little bit in future slides about how you can kind of seamlessly read in Parquet files or also read in other semi-structured data sources like JSON. And then finally, we have this last component, which is our Hive support. And this is actually a relatively thin layer. But what it does is it's going to interact with the Metastore, HQL, SERDES. A note here on the Hive layer, this is a separate component that is an optional dependency. So if you're compiling your own version of Spark and you want to use Hive, you need to set an environmental variable, Spark Hive equals true, before compiling the Spark distribution. So this is all documented in the programmer's guide. But because Hive has so many dependencies, we didn't want to pull it into every Spark program that anybody wrote. So we kind of omit it by default. So a big question that we get with Spark SQL is, what about Shark? So we've been talking about this at the whole Spark Summit, but in case you haven't heard, Shark was kind of the first project that allowed you to do SQL on top of Spark, and it ran much faster than Hive because we were able to kind of leverage in-memory computation. But one of the key disadvantages was it was very tightly coupled with the Hive architecture. And this led to a couple of problems. First of all, there was limited integration with other Spark programs. So even though we were doing RDD operations underneath the covers, it was relatively difficult to kind of use those alongside other RDDs in your own programs. And then the other kind of big problem was the Hive optimizer wasn't designed for Spark. It was designed for MapReduce. We found it fairly difficult to extend and kind of add in new optimizations that were Spark specific. And so the idea of Spark SQL was to take the best parts of Shark, so the in-memory columnar storage, which I'll talk about some, and all of the ability to interact with Hive, and replace the rest with kind of a clean rewrite of the rest of the system. And the things that you're going to get in contrast to Shark are this RDD-aware optimizer, which kind of allows us to integrate more closely with other Spark programs, and then also these interfaces. So, the existing users of Shark don't despair. We've got a plan moving forward. So there's not going to be any more active development of the Shark code base moving forward. But we've now ported all of the various interfaces into Spark SQL. So if you're using the existing JDBC server, you can use the same drivers to talk to Spark SQL over the same protocol. This is a relatively new feature that we just did a preview release of on Monday. And the idea is, so if you want to check it out now, the GitHub branch is up here. You can check that out and compile it. And we will be including this in the 1.1 release of Spark. Here's kind of the details of how you're going to use it. It's very similar to if you were using Shark. I mean, a lot of this code is actually just ported over to use the Spark SQL backend instead. But basically, you can start up the server. That we put a script in the sbin directory, just like the rest of the server components of Spark. This will be included in the distribution by default. And then once you've started this server, you can now use any JDBC client to talk to it. So Beeline is one example. And here's kind of the connection string if you just want to try it out on your own computer. And then we also have an ODBC driver as well if you want to connect Tableau or MicroStrategy or any of these other systems into Spark SQL. Okay, now that we've covered that bookkeeping and we've given some background, let's actually dive into what makes Spark SQL different from just writing a normal Spark program. And a key idea here is the notion of schema. So when I say schema, I'm talking about the actual the shape of your data. So the columns and the data types. So instead of looking at your RDD as just an opaque collection of objects that we're going to do kind of these coarse-grained transformations on. So you see in this example, we've got a partitioned collection of user objects, but Spark has no idea what's actually stored inside of each of those user objects. It's kind of naively serializing it and shipping it over to other machines. In contrast, when you create a schema RDD, we actually know, and we kind of break this down into tables. So we know, that you've got a name column, that's a string. You've got an age column, that's an integer. And a key difference here is now you're actually doing declarative transformations. So when I say declarative, what I mean is that you're not telling me how to execute the query. You're just telling me what data you want back, and it's up to the system to figure out how to execute it. So that means that I know that all you want is the name column, so I'm going to filter all of the other columns out immediately. And if we're using an efficient format like Parquet, we'll automatically configure the input format to only read the columns that we need off of the disk. And you don't need to do that because all you've done is kind of given us the structure of the computation you want. And a really important thing to schema RDDs is that this isn't an either or. You can kind of go back and forth between a normal RDD and a schema RDD relatively seamlessly. And that was kind of a key goal when we designed this. And so what you're really getting with Spark SQL is this unified data abstraction, where you can write programs in Python, Scala, Java using the existing Spark APIs, but you can also write in higher level APIs like HiveQL, and we're working in the future, that's why this is a dotted line, on SQL 92 support as well. And through this unified interface, one of our goals now is to provide access to a variety of different structured data sources. So the ones that we support today are Parquet, JSON, and Hive. We're also working on CSV and Cassandra. There's interest in HBase. So kind of our goal long term is to make schema RDD the narrow waist by which you can access data in other systems. So how do you actually use Spark SQL? So I'm going to do all these examples in Python, but all of this code will work in Java and Scala as well. Basically, the first step, those of you who are obviously already familiar with Spark programs, in a very similar way to creating a Spark context, you're going to create something called a SQL context. The SQL context is what holds the catalog, your list of tables. It kind of actually drives the query optimization flow. And so basically, all you need to create a SQL context is a Spark context. It just wraps around it and extends it with all of these extra relational functionalities. So for these examples, basically, I'm going to start with a relatively simple data set. This is included with the Spark distribution, so you can do all of these examples from the Spark shell by default. But just consider that I've got some text file, and that text file is just filled with names and ages separated by a comma. And I want to run SQL queries over this data. So the first step is going to be I want to turn this kind of standard RDD, this text file that I'm going to load in, into a relation. So in order to do that, we need to break it up into its parts and assign names to each of the different elements of data. So on the first line here, I'm using standard Spark context to read this in as a text file. And I'm getting back an RDD that has one line as each element. And now I'm going to do kind of standard Spark text processing on it to split it up by commas, and then actually turn this into a Python dictionary. So in this case, I'm basically creating a dictionary. We've got a name key with the value of the first element of each line of that text file. I'm also doing some data conversions here, so you can see the age column is going to be an int. And as soon as I have an RDD of dictionaries, I'm basically already at a schema RDD. All I need to do is tell it to infer the schema. So I just pass that into the SQL context, and it's going to return a schema RDD, where basically what we've done in this case is we go and we look at the first row of your data, and we look at all of the columns that are there and all of the data types, and we use that to infer the schema of the entire data set. And then we'll convert it into our more efficient schema RDD representation internally. And as soon as you've got a schema RDD, any type of schema RDD, you can register it as a table. So I'm going to assign a new name to this, which is people. And just to kind of go through, you can actually also do this in the other languages, like I mentioned. So in Scala, the syntax is slightly different. Basically, what you're going to do is you're going to create a case class. And so you just create a case class with all of the names and types of all of the data items in your data set. A couple of notes about the case class interface. You can actually put nested case classes. So if you want to have a more complicated data structure, you can put sequences in there as well if you've got repeated elements. And then basically from there, the example is almost exactly the same. We do standard Spark text processing. We turn it into a collection of person objects. And the cool thing in Scala is anytime you have an RDD that is made up of case classes, as long as I've done this import of SQL context, which puts some implicit conversions into scope, your RDDs of case classes can kind of automatically become schema RDDs. We use a trick called compile time reflection to actually get something called a type tag, which tells us the schema of your data set, and then we can automatically convert it into a table. So you can see here, even though this is just a standard RDD, when I call register as table on it, since that's not an operation you can do on a normal RDD, the Scala compiler implicitly converts it into a schema RDD. And so, once again, now we've got this people table, just like in Python. And you could do the same thing in Java. I won't spend too much time on this, but basically, in a very similar way to Scala, you create a Java bean. And a Java bean is just a standard Java class that implements serializable and has getters and setters for all of the different data items inside of it. And so you create your Java bean, you fill it with the data, and now you can just call SQL context apply schema to turn it into a schema RDD. So now we've seen how to take any data set in any of our various Spark supported languages and turn it into a schema RDD and register it as a table. So why would we want to do that? What can we do now that we've done this conversion? So once you've created something as a table, now you can register or you can query it from SQL. So I've just got this SQL query here that's going to find all of the teenagers in our data set, so anyone whose age is between 13 and 19, and I only want their age. So basically, you just write it out as a SQL query. I can reference any table that I've registered. And then the cool thing here is teenagers is actually also an RDD. So SQL in this case is behaving quite a bit like the Spark programs that you're used to. So the SQL command is lazy. All it's done is build up the lineage. And what you're getting back is an RDD. So if I want to do more SQL on it, I can. I can take the results of this SQL query and register it as a table again. But I can also just use it as a standard RDD. So you can see in this case, I'm just going to pass a Lambda function, which is going to process this in parallel. So unlike if you're using a kind of more standard database and doing JDBC and kind of bringing all the data back to your local machine before doing processing on it, since this is still an RDD, the results of this SQL query, if they're giant, are still partitioned across the data set, or across your cluster. And so you still get kind of any parallelism to any operations you apply on top of those results. So, of course, this is Spark, and so we want to be able to make efficient use of all of the memory that we've got in our cluster. So we actually ported the Shark in-memory columnar format so that we could also use it inside of Spark SQL. So there's a couple of advantages to this. First, let me kind of explain what I mean when I say we're storing the data in an in-memory columnar format. So when you do standard Spark caching, what it's going to do is it's actually just going to hold on to all the JVM objects and keep them around in case you run more queries on them. The downside to this is that if you've got a really big data set, that's a lot of objects to keep live on the JVM's heap, and that can actually be pretty expensive for the garbage collector. So since we understand the data set, since we know all of these different types, we know how to break it up into its individual columns, we can do a better job than Spark alone can. And so what we actually do is for each partition, for each column, we allocate one giant byte buffer in memory, and we serialize out that column into that byte buffer. We can also play tricks, like if it's an integer column, we kind of shrink it down to the smallest possible integer using like zigzag encoding or delta encoding to only store the differences between integers. We have dictionaries. And the cool thing is we automatically select the best compression there. So even if you're not using SQL, changing your data into a schema RDD can let you cache it more efficiently inside of Spark. And, and we kind of do all of this automatically. The way that you cache a table right now is just by calling cache table and then passing in the name of the table. Just like a Spark cache, this is a lazy operation. Nothing happens when you do this. But then the next time you access that table, once we compute each of the partitions, we'll keep them around in memory. Another note here, this is actually an open JIRA, something we're trying to fix. But if you've got a schema RDD and you call .cache on that, it is not using the in-memory columnar cache. It's actually just keeping all of those row objects around. So you need to register it as a table and cache it as a table. That's something we hope to fix in the near future. So kind of a key thing here is this should be more than just SQL. You should be able to kind of mix in programming alongside your SQL commands. This is something we've kind of been demoing the whole summit. It was part of Ali's talk at the beginning. But just I want to walk through this example a little bit more. Once again, this works in both, this also works in Scala. This is a Python example. Basically, the idea is you should be able to take any Lambda function, assign a name to it, and then seamlessly use it inside of future SQL queries. So in this case, I've written a really simple UDF. Basically, I'm just going to take a regular expression, and I'm going to try and find all of the instances of that regular expression inside of the text that you pass into me. Yes?
I couldn't make this working with Scala. I couldn't find this function in the...
Oh, so OK, yeah, let me clarify some things. This is a hot up-and-coming feature. This is bleeding edge. You actually need to merge in a pull request to get this right now. This will be part of the 1.1 release of Spark SQL. So yeah, thank you for pointing that out. This is not included in the distribution you're using today for your exercises, but this is a feature we're adding for 1.1. Is there another question?
Yes. What is your in-memory columnar format? Is that in PAX format or in this like?
I mean, it's not in PAX. It's our own custom thing. It's the same one as Shark. And yeah, and I'm happy to go into more dirty details afterwards. Just come find me. Okay, so a couple of other things about registering Lambda functions as UDFs. In Python, we don't have any type information. So we assume that the result is going to be a string, and if it's not, we convert it to a string. But you can kind of specify the return type if you want. So there's an optional argument to register function. So I would just say return type equals int if I want to return an int and I want to actually get a nice typed int out in SQL. In Scala, we use type tags once again to just infer this. The compiler gives us that information. And as soon as you've registered it as a function, you can use it immediately inside of SQL. And another kind of cool trick, you can actually register UDFs in Python and then use them in Scala and kind of go back and forth. So let's talk a little bit more about SQL and mixing with other parts of the Spark stack. So one of the really cool things about Spark is that we've got all of these other libraries, and kind of a key focus moving forward for us is going to be allowing you to go back and forth between the different libraries very easily. So often your actual data pipeline that you want to run is more than just doing SQL or more than just doing machine learning. You need to import some data, munge it in some way, then do machine learning on it, then output it somewhere. So in this example, basically, you can consider I've got 2 data sets. I've got a collection of users and some demographic data about them, and I've got a list of actions that past users have taken. And I want to guess which users are likely to take some actions in the future based on this model that I can build. So we can use SQL for what it's good at, joining data, doing filtering. It's kind of like SQL's bread and butter. Getting data out of Hive. So let's say you've got this data stored in some other system. Kind of we'll take care of all the data conversions for you. So we run SQL. We get back an RDD here called training data table. But now we need to munge it into the format that MLlib is expecting. They don't want rows back. They want kind of nice, efficient arrays of doubles and things like that. So we have this command called featureize, which just converts each row into a labeled point. A thing that you'll notice is in the Python API, I can actually access all of the columns by name. In the Scala API, you would do .getRow, or I'm sorry, .getInt or .getString, and then give it the column ordinal that you want back. And same thing in the Java API. And so once we've done this, once I've written this Lambda function, I can now just assign it to, or I can just map over the data set to do this conversion. And once I've got it in the format that MLlib expects, I can just drop it directly into this logistic regression algorithm. Yes? Yeah, all the slides will be available. I think they're actually already posted online, but yeah, they'll definitely all be up online. Cool. So another big part about Spark SQL is actually the ability to access different data sources. And so one of the first ones that we've implemented is Hive support. So really our goal here is that you should be able to use most of the things from the Hive ecosystem seamlessly with inside of Spark SQL. So part of this is you can actually write your queries in HiveQL. So if you create a Hive context, there's actually two different methods for executing SQL. You can either do .hql and pass it queries written in the Hive query language, or you can do .sql and run them in a simpler subset of SQL. Kind of the goal here to have this separation is long term, we're going to maintain compatibility with HiveQL in the HiveQL method, and in the SQL method, we're going to be aiming for something that's like SQL 92++. In terms of actual usage today, what I'll say is the HiveQL parser is significantly more complete. So you'll be able to do most operations inside of HiveQL, and a big part of that is we have wrappers for UDFs. So Hive has a relatively large UDF collection already, and you can seamlessly use any of those from inside of a Hive context. The other things that we do, though, is we also interact with the metastore. So basically, just by taking the hive-site.xml file from your existing Hive installation and dropping it in the configuration directory of Spark, we'll then connect to the metastore and ask it where all of the tables are located, what your schema is, kind of those sorts of configuration things, and you can access those then automatically from inside of Spark SQL. And we support all of the SERDs as well, which actually lets you kind of read this data in and parse it into our format. So like I said, all you need to do to read data from Hive is instead of creating a SQL context, you create this subclass of it called a Hive context. And once you've got a Hive context, you've got these additional methods like HQL. You can even do things like run DDL commands. So when you run a query, we're going to execute that inside of Spark. But when you run a DDL command, that's just changing the metastore. It's not actually computing any answers. And so we just pass that directly back to Hive, and it runs exactly as it would if you gave it to Hive. Other notes, kind of just like Spark, things like DDL are actions, so they happen immediately, and queries are lazy. They're just kind of transformations, and so those just build up lineage. Another data source that we support, in addition to Hive, is Parquet. And we say we kind of have native support here because you can do it directly with a SQL context without any other libraries. Parquet is another columnar storage format, so an advantage here is if you've got really wide data, but you're going to be reading it many times, accessing only a subset of the columns, Parquet can give you huge speedups. So I did a demo yesterday where basically I had, I think it was 5-something terabytes of data in JSON. I stored it out into Parquet. That made it significantly smaller. I think it cut it down to hundreds of gigabytes instead. And basically then what I could do is, even though it was stored off S3, I could run queries that pulled out a single column in a minute. So, and from 10 minutes to just decompress the data and do no other work, to a minute to just actually read it out and do interesting joins and aggregations on top of it. So you can get pretty big speedups by using these more efficient formats. And another big thing is that Parquet is self-describing. So I think a common nightmare is when I write my data out as something like CSV or TSV, you're responsible for remembering the columns. When you load it back in, you have to kind of remember what the order was. If one of your coworkers adds a column, it's going to break your script. The nice thing about using these self-describing formats where we actually preserve the schema is the column names are actually encoded along with the data. So if you add columns or reorder columns, all of your SQL queries will still work because you're referencing the data by name and not by ordinal. And so if you write an RDD out as a Parquet file and read it back in, all of that kind of automatically comes along. So just to kind of walk through that a little bit more, if I take my original schema RDD from the last example, this people table, I can save it as a Parquet file, so that kind of writes it out just like any of the other save as commands in Spark. But then when I read it back in using a SQL context, what I get back is a schema RDD. And so I can immediately take that result of loading in a Parquet file and register it as a table. and then I can run SQL queries over it right away. So this is kind of the exact same example, but reading data out of Parquet instead of out of a text file where I've done some munging and conversions. So yeah, so the question was, do we just store the whole table or do we filter by columns based on the queries you're going to run? So when you do save as Parquet file, we store out all of the data in a columnar format. When I actually run this SQL query here, so when I actually do this load Parquet file, no work has been done. All I've remembered is kind of logically I want to load this Parquet file. And so when I register it as a table, still no work has been done, and I'm just remembering the location of that Parquet file. And it's not until you actually perform an action on the result of a SQL query that we read any data off the disk. And so at this point, I know that all I need is the name and the age column, and I will only deserialize those columns from disk. And that column pushdown happens automatically by using Spark SQL in the Parquet format. Does that answer? Awesome.
So if I'm starting a new project, Parquet will be the way to go.
I mean, yeah, this is the fastest, simplest way to use Spark SQL at the moment. If you've got existing data in Hive, though, I mean, I think that there's trade-offs, but like right now, this is the easiest way. Yes. Oh, sorry. You okay.
So if the data is changing within the Parquet file by another process, which one of those steps do you repeat? Do you reload it?
Yeah. So well, that's a good question. Yeah, sorry. So the question was, if the Parquet data is changing by another process, what would you do to kind of reload that new data? So let me give some cautions here. It's in general not safe to have multiple processes writing to like the same directory in HDFS. They might clobber each other. In fact, by default, Spark won't allow you to write out to a directory that already exists to prevent this. There are some experimental mechanisms in Parquet to allow you to append data to an existing thing, but it's up to you to do the coordination that two people don't try to do that at once. You should reload the Parquet file and re-register it as a table if you want to pick up any updates. Depending on whether or not you've read the data before, it might not be cached, so you might get new data just by kind of running a query. But if you want to be sure that you're going to get the newest data, you should reload Parquet and re-register it as a table. Remember, that's like a pretty cheap operation because all you're doing is like updating this pointer in your catalog. Was there? Yes.
So in the case of Scala, if I have a case class I'm using, who I define a table as in the Parquet or JSON or something like that, is there a way to get that back into a strongly typed object so I'm not using symbols?
Yeah, that's a really good question. So the question was, if I'm in Scala and I create a case class and I serialize that out as Parquet and then I load it back in, can I get back those strongly typed objects? And the answer is that's open research. I'm actually working with a couple of grad students in Martin Odersky's group on doing this sort of type refinement. They emailed me this morning with a prototype, but it's very experimental. It's using macro features that like Martin isn't promising to keep inside of the compiler. But as soon as we have something working, I'll certainly like follow me on Twitter because I'll certainly be tweeting about it. So yeah, that is something I would love to get more type safety into the language, both for kind of when you read objects back in and even just when you access them. But that's experimental and not something that you're going to be able to do immediately. Yes. Yes, so we do support nested data. We support nested data for Parquet. That is a new feature that was not in the 1.0 release, but is in the 1.01 release and will be in 1.1 as well. So if you want nested support, you need to download from GitHub and compile it now. But we do support nested data kind of both in Parquet and in Hive. And the HQL query language also supports nested data. So if you want to access nested fields, you can just use dot notation. You can use brackets to go into arrays. Our goal here is to kind of seamlessly mix programming with SQL. So it's kind of that's why we're doing like SQL 92++ in general. Okay. So I just want to talk real quickly about some of the features that are slated for the 1.1 release. I talked about these in my talk the other day, so if you want to know more about them, check out the video, which will be up on the website, I think in a couple of weeks. Some things that we're working on, I think really the big focuses for the 1.1 release are going to be performance and stability. So we want to make this as fast of a system as possible, and we've got a bunch of ideas about how to do that. One of them is runtime code generation. So basically what we're doing here is instead of interpreting the expressions, I say select A plus B, instead of interpreting A plus B, I'm actually at runtime, when you write your query, going to invoke the Scala compiler and compile custom bytecode to build all of the rows. And it turns out this gives you this is basically like hand tuning your Spark programs, but without having to write any code. And so we're hoping to merge that in. Language integrated UDFs, like I said, that's also kind of a feature that we're hoping to add in for 1.1. Both of these are available if you want to be on the bleeding edge. These are both already up as pull requests against Apache Spark. So you can check them out and pull them into your own branch if you want to play around with these features. In general, we try to do all of our development out in the open. As soon as something is even like half baked, I put it up there, and then we kind of iterate on it until it's ready to merge into master. Other things we're playing around with: auto selection of broadcast or map side joins. So in this case, if you've got a giant table and a really tiny table, instead of shuffling all of the data, we're just going to take that tiny table and ship it out to all of the machines. And so you avoid shuffling the big table, which is a huge performance win. And our goal is to basically let you set a threshold by which anything smaller than that threshold we automatically broadcast. And then also JSON and nested parquet support. So both of these are already in master. They'll be in 1.01, but they're also going to be in the 1.1 release. And then, like I said, many other performance and stability improvements. We've been fixing quite a few things. So just a real quick preview of what we think all of these performance changes are going to allow us to do. This was basically what we did was we took a development branch that included all of these features, and we tried comparing it to the old Shark code base. And basically what you'll see is that kind of by some of the tricks we're playing, we're actually faster than Shark in all cases, and in some cases up to 8 times as fast. So I'm excited for the things that are in store. And so that's actually my talk, but I'm happy to take any more questions if there are any. Oh, I'm out of time.
All right. Sorry, we're cutting Michael off because we're about 15 or 20 minutes behind. So we're going to move straight into the next talk. TD is going to do streaming. If you guys have questions, Michael's around. He's available to you. And obviously, when we're doing labs later, he'll be here, and you can pull him aside then. All right, 1 second here. We've got some technical issues. So for any of you guys who ever give talks at conferences and insist on using your own laptop, remember this moment right now. Does he not have that? There you go. It's over there. Close that one.
Is that the wrong talk that I transferred?
Well, no, because the other one's already full screen. That's why.
Oh man. Okay.
Hmm?
Yep. Okay, finally. Woohoo! We can process terabytes and petabytes of data, but still can't get a laptop to plug and play. Yeah, technology. Anyways, finally, so I am TD. That's my initials, and I'm essentially a core committer of Spark, and I'm the lead developer in Spark Streaming. So you will probably find most of my commits going into Spark Streaming, and I'm on leave currently from the PhD program in UC Berkeley. Okay, so let me start with a very brief history of why we built, of what is Spark Streaming, the what and the why. And it's essentially, just like Spark SQL, it's essentially an extension of the Spark API. It started as a research project back in 2012, where we started building this thing. And for building this thing, we actually took Spark, the existing version of Spark, and tore out all the internals of Spark to make it 10 times faster than what it was back then. And we released the first version of it in early 2013 and as an alpha, and then early 2014 it graduated with Spark 0.9. It graduated as a non-alpha full-time thing. So why did we build it? Now, back in 2012, we started looking around and asked people Spark what more do they need from Spark, and also generally looked around, and we found that there are lots of applications out there which actually want to process data in real time. As in, there's data coming in from live data sources, and you want to get results from that data as soon as possible. For example, you want to monitor your websites or a set of websites or your sensor nodes, etc., and figure out whether they're working properly or not. There's no point if you get to know that 1 hour later after you've run your Hadoop jobs and stuff, because the harm is already done. Similarly, you want to do fraud detection as soon as the fraud happens. You want to do GAD monetization, change stuff as soon as things are happening. So for this kind of stuff, the common theme across all of this is that there was a need for a distributed stream processing system that can receive all these data streams and convert that data into value in real time. And for that, obviously, you need the system to be scalable to hundreds of nodes, as well as achieve low latency. And we found that a latency of the order of seconds covers a lot, probably around 90% of the most use cases that people were asking for. Additionally, we also found that it's important to deal with failures. If you're working in a cluster environment, you're probably going to have your worker nodes failing and stuff. A stream processing system needs to recover efficiently from failures while giving guarantees on what the result of the data is despite of failures. And another important fact that we found is that it should integrate well with batch processing and stream processing, batch processing and interactive processing systems. Let me elaborate that. Why is that the case? So we asked many companies, and we found that many such environments in data processing environments in companies actually have the requirement that the same data that they are going to process in real time, they're also going to do post-processing on that data offline. For example, you want to process the same data and generate monthly reports, yearly reports. So for that, the same data needs to be processed in two different scenarios. One, real time, as well as a larger volume of data in offline. Now, there doesn't or exist any framework that could do both together. For both process terabytes, petabytes of data over large volumes of data with, let's say, low latency hours, as well as do hundreds of megabytes per second with low latency stream processing. So the way people dealt with in the existing technology was that people built two different stacks. One, a Hadoop stack or equivalent stack, which used to process terabytes, petabytes of data, the other, the real time. Now, the problem with this dual stack model is that you have to express your computation in two different models. You have to deal with these two different programming models, two different execution models. You have to deal with two different kinds of bugs. You have to deal with, from operational point of view, you have to deal with two different stacks completely, which is a huge headache. So we thought of simplifying it. Another challenge is that achieving fault tolerance in a streaming environment is actually not that easy. It's actually a hard technical challenge. For example, the way traditionally stream processing has been done is using this model where you have a worker of nodes with a streaming pipeline set up between these workers, where every worker is doing one computation. Let's say a worker is supposed to filter the stream and forward it to the next worker. Now, if you want to do something like a running count of how many records the stream has seen, the way it is done is you have a mutable state in the memory of the worker. There is basically a counter, which the counter is incremented every time a record is forwarded to the next node. That's how people have been doing it in traditionally. But the problem with this model is that the moment the worker dies, that counter in the memory is lost. And so you might suddenly find your count of the number of records received till now suddenly 0, which is not good. And dealing with this kind of idiosyncrasies is really a hard challenge. And so making stream processing fault tolerant is actually is actually an academic challenge, which motivated us to actually take up this research project, and thus we created Spark Streaming. Now, just to give you an example of how other systems deal with this, for example, you might have heard of this popular system called Storm. The guarantees that Storm gives is that it will process every record at least once. So it is not exactly once. So what may happen is that if you're counting your records, you might easily get double counted. And in practice, it actually happens so. And again, if you are maintaining any arbitrary mutable state, your node dies, your state is gone. And so real systems actually have these problems. As a follow-up to Storm, there was another system written on top of it, Storm, called Trident, which uses transactions to update this mutable state to make sure to get the exactly once processing model. But what we have heard from many developers is that this per state transactions actually causes a huge impact on throughput. So many developers actually don't use this Trident to achieve the throughput they desire. So we ended up building Spark Streaming. And the idea behind Spark Streaming is actually very simple. You take a streaming computation and express it as a sequence of very small deterministic batch jobs. So you have your data stream coming in. What Spark Streaming will do is that it will divide your data stream into batches of X seconds. Now this X is configurable by the developer. Once it divides the data stream into batches of X seconds, it actually forwards those batches of data to Spark. Spark processes that and gives out the results also in batches. And with this very high-level model, now the real technical challenge is to allow this sort of batched processing at a very low latency of the order of seconds. And this was not exactly possible to do of the order of seconds in other existing systems. Like you could, at a high level, you could use this model in Hadoop, but you probably will not be able to do it in the order of seconds. You'll probably be able to do it, say, 10 minutes at the best. So but in Spark and Spark Streaming, we can do it because Spark is a really, really fast processing engine, which allows jobs to be run in the order of milliseconds, which allows us to process data in the order of seconds, which allowed us to build Spark Streaming on top of Spark. And also, an additional advantage is that since it's built on this batch processing platform, we expect it to be much easier to integrate batch and stream processing together in the same place. So you have already heard about RDDs from Reynold's talk. In Spark Streaming, we provide an additional abstraction over RDD, and it's called dstream, which is the short for discretized streams. And the idea is that a dstream is essentially a sequence of RDDs representing a stream of data. Now, this dstream can either be created from your input data source, or by transforming other existing D streams. It's kind of similar to how the RDD model works, where you can either create an RDD from a Hadoop file or by transforming other RDDs. So let's see it in action, how a streaming program looks like. So similar to a Spark program with a Spark context, you have to first create something called a streaming context, where you specify what is the batch size that you're going to use. In this case, we are using 1 second. And to create a streaming context, you need a Spark context as well. So I'm assuming that that has already been created. So once you create a streaming context, that gives you access to these library of utilities that allows you to create new input stream from different sources. In this case, let's say, since I want to count hashtags or get the hashtags from Twitter, we're going to use Twitter util to create a Twitter dstream, which essentially creates a new input dstream. And what happens underneath is that as data is received from the Twitter streaming API, the data is chunked into batches, and the batches of data is stored in Spark's workers' memory as RDDs. Next, we want to do some transformation over these tweets. Let's say we want to get the hashtags out of it. So for that, we apply this transformation flat map to get the multiple hashtags from each of the tweet. And this transformation essentially creates a new dstream. And underneath what the system, when you run this whole program, what the system would do is for every batch of data that is received, it will do these flat map operation on that RDD underneath and create new RDDs. And this new sequence of RDDs will essentially form the new dstream. By the way, feel free to ask questions. I'm happy to have this session interactive. Yes, back. Sorry?
Maybe you'll show this, but are you going to show how people interact with it over time and use the hashtag?
So I don't have a demo planned for this session right now. So the way, let me just add on to this, and that may probably answer your question. And finally, once you have done all your data transformations, you're going to do something with the data, maybe push it out to HDFS. Let's say for that we have this operation called save as Hadoop files, which saves each bat of processed data, in this case hashtags, to as Hadoop files. And these type of operations are called output operations. And it's not just saving to, what it essentially does is saving to HDFS. And not just saving as HDFS, you can do arbitrary stuff with the transformed data using this operation called for each RDD, which gives you directly access to the RDD. And you can do whatever you want in that. Either push it out to some external database, let's say Cassandra. You can directly push it out to a dashboard website to update your dashboard, whatever you want. Now, the way this lazy, okay, yeah, sure. I can barely see. Oh, there you are.
Does it make sense to say that you want smaller batches to reduce latency?
Yes, exactly. So to reduce the latency, you want to be able to process things in smaller batches. The smaller the batch. Yeah. No, that's not true. So if you have, I mean, these are two independent parameters: the batch size and the size of the cluster. Yes. Yes. So the question was that if your batch size is small, does it mean it's better to have a smaller cluster? Is that, I'm guessing that's the question, is it? Okay. I could barely hear. Thanks. If you want to reduce latency, does it benefit from adding nodes to your cluster? Yes, absolutely right. So more nodes in the cluster, the more parallelism that you can take advantage of, the faster you can process, the lower the latency you can achieve by reducing the processing things faster. Even if the batch size is small, you can process things faster with a larger cluster. Yes. And so, and and the way this streaming program works is that this all this similar to the Spark's philosophy, all this computation is actually lazy. So while the system is executing these commands on the screen, no operation is happening. You need to finally do streaming context dot start for the computation to actually start. And you're going to see that in action in your tutorial itself, so you'll get a sense of how this works in actions. Moving on, so you can write this computation in both Scala and Java, and the Python API is in the works. It'll come soon. And for Java, you obviously have to use these function objects rather than the simple Scala API. What you get along with these D streams is, yeah, questions. So when I do saying save as Hadoop files, so the question is that when I use save as Hadoop files, what exactly is being saved? So if you see the example carefully, I'm calling hashtags.save as Hadoop files. Okay, so hashtags is essentially the D stream that contains all the hashtags that are being received, right? So each batch of hashtags is going to be saved as a different file. Yes. Yes. So using it, yeah, each batch of hashtags will be written to a different file. So you open the file, close the file. Yes. So yes, it's not recommended. So this is just an example. It's not entirely recommended to do this really at a very low latency. Typically what people use is save as Hadoop file with and use that to actually write it to Cassandra and use the same API to write it to Cassandra, in which case it is, which works pretty well. So what question was what formats are supported through this? So we are using the Spark's underlying API for writing to arbitrary Hadoop files. So whatever input format or output format is supported through HDFS API, it is, all that is supported through this. One last question before I move on. Yes, so the question was whether the data in these small RDDs in the batches are partitioned or not. Yes, absolutely. Yeah. Moving on. So what you also get out of these transformations, out of the DStream API are window-based transformations where you can specify that give me the data over the last, let's say, 1 minute, and move the window every 5 seconds, let's say. So so what happens underneath is essentially the sliding window that operates on the D stream. And this window is operation is defined based on 2 parameters. One is the length of the window, in this case 1 minute, and second, how frequently does the window move. So in which case, It is, in this case, it is 5 seconds. I can barely see the screen on my system, which is why I'm having to peek at the big screen. Anyway, better. Okay. Now, using this window operation, you can do a lot of complex event processing type operations within the D stream itself, and there are multiple flavors of this window operations. You can do reduce by window, reduce by key and window, and all these different flavors of window operations are there. You can look up the Spark streaming docs for that. Also, you can do arbitrary stateful computations where you can specify that for any key, you want to maintain a continuous state that you want to continuously update as data comes in. To take a very slightly weird example, where let's say you want to monitor Twitter, and for every user in the Twitterverse, you want to maintain what mood the user is in. I know it sounds creepy, but let's say to do that, all you need to do is essentially define this function called update mood, where given the previous state or of the user and the new tweets from that user, you can calculate the new mood the user is in. And once you have defined this function, you can use that function in this dstream operation called update state by key, where you apply this function to it, and the system will take care of actually taking the new tweets for that user. In this case, the user is the key. And take the new data of that user, apply the function on the previous state, and get the new state. And the system will continuously do this operation over and over again underneath. So it's pretty easy to plug in arbitrary stateful computations in this model. Yes? What goes underneath? So underneath, essentially, this computation essentially boils down to a number of joins happening on every batch, where the new data is partitioned based on the key, and the existing state which is also an RDD kept in the memory, is partitioned based on the same key and joined together to combine the new state, the old state, the new tweets, and generate the new state. Now, regarding how it happens, occurs underneath, you can actually look at the source code. It's not too complex a source code to look at it, but I can talk about it offline on what are the implications of that. Let me move on. The third thing that I want to discuss, highlight in the dstream API, is that you can there's this operation called transform, which gives you access to every RDD in the dstream directly. And you can apply any RDD to RDD transformation on each RDD of a dstream. And this essentially allows you to intermix arbitrary batch-like computation with streaming-like computations. For example, let's say you have the tweet stream, and you want to essentially filter out tweets that have some spam hashtag in it. And to do that, you have a file in HDFS which has all the spam hashtags, and you want to take the stream and join it with the file. And that you can do very easily using this transform function as shown, where you basically define the function that for every tweets RDD from the tweets D stream, I'm going to join it with this spam file and filter out the results after the join. And so this this allows you to basically view the stream both sometimes as a point of view of a stream, or sometimes as the point of view of pure sequence of RDDs, and you can do arbitrary RDD computations on top of it. And this duality of dstream and RDDs gives you a lot of power. For example, you can combine live data stream with historical data. Let's say you have some historical data, and you have computed data models with it by running Spark jobs on it. You can take the data model that you have learned and apply it on a live data stream, just like the way I've shown spam hashtags being used to filter out live data stream. You can combine streaming with arbitrary machine learning and graphics and all these algorithms that are also come as parts of Spark. So you can do offline learning and then online prediction. You can also do online learning and prediction using this transform. Then you can also query streaming data using SQL. So and to show this, to show how that can be done, I'm going to refer to the Databricks keynote demo. So how many people here actually have seen the Databricks keynote demo that we showed yesterday? Okay, I'm guessing most of you. Just for those who have not seen the keynote demo, what we had shown is how using the Databricks product we can actually take the stream and a live Twitter stream, and we can apply machine learning algorithms on top of it, and then also apply SQL queries on top of it. And what I'm going to do is essentially show the code the simple code that was running as part of the demo. And so what we had done essentially is create a new streaming context and also a SQL context that Michael talked about. Create a Twitter stream, apply a filter to filter out only English streams, English tweets, apply a window operation on it. And essentially what we did after that is that for each of the RDD, we registered the RDD as a table in the SQL context. And so as the D stream was running, last 1 minute of tweets was essentially registered as a ever-changing table in the SQL context, and which allowed us to then finally run SQL queries on the last 60 seconds of data. And that essentially was the magic that you can do on the open source right now, minus the visualizations and stuff. So this shows how easy it is to combine different of the components for having with streaming and Spark SQL all of it together. Moving on, the last but not the least, the big advantage of having this unified stack is that you can do combined interactive batch and all of it together without having to change the code. You can figure out stuff interactively, write a Spark program to do it on much larger amount of data, and pretty much the same amount of very similarly looking code. You can plug it use these streams to get real-time data processing right out of the box. Finally, a small point about the fault tolerance. The way we handle fault tolerance to give you stronger guarantees than what other systems can give is that the raw input data is actually replicated in Spark's memory. And so what allows us to do is that if any of the worker node dies, so the data is replicated, if any of the worker node dies, since the data is replicated on at least 2 machines, we can recompute automatically the transform data, in this case, let's say the hashtags that was lost, recomputed back again from the raw input data. And so your computation will never be affected by any failure of any of the workers. And as a result, all the transformations that we do, counting everything, have exactly one's property, no matter there is a worker failure or not. Out of the box, we provide these. Oh, here's a question. That's a good question. We have exactly one's properties for any data transformations. If you're pushing the data out to a database or some arbitrary database, then you have to make sure to get exactly one's properties by doing idempotent updates to the database. That's a good question, Remy. Anyway, so out of the box, we get input sources of Kafka, Flume, Akka actors, raw TCP sockets, plain old HDFS, and Twitter, of course. But it's very easy to write your own custom receiver. There's a very simple receiver API where all you need to specify is what to do when the receiver is started and what to do when the receiver is stopped. And that's it. So people have been writing their own receivers using that API. And also for testing, if you may not have a data stream source, but you may want to test your streaming program with arbitrary data. So you can generate your own sequence of RDDs from, let's say, some offline log files and push them down a streaming program as if it's a stream. So that can also be done using something called a queue stream. So that is very beneficial while testing. Anyways, to wrap up, where are we going in the future? So in future, we are planning for better, tighter integration between with SQL, with MLlib. We were planning for having online prediction algorithms right out of the box in MLlib. GraphX, Ankur later might talk about it. We also have planning further improved integration with different sources like Amazon Kinesis, etc. Improved control over data rates so that you can control your streaming program a lot better, and of course Python API, which I touched upon earlier. Anyways, one thing to note about today's tutorial. So in today's tutorial, we're going to process Twitter data stream to find most popular hashtags over a window. But for this, you need to actually provide a Twitter account because that's only way to access the Twitter data stream. But so for that, you need to set up a few keys. All the instructions are given in the tutorial. But the thing to keep in mind is that you will now have to enter your password anywhere for the tutorial. You just have to enter the keys, and once your tutorial is over, you can easily delete off all the keys and your account will never be compromised. So if you're ever concerned while seeing the web page that, whoa, whether I'm entering my Twitter, what's gonna happen? You don't have to worry, you can delete off the keys and your account will be safe. Finally, to conclude, I have not covered a lot of the finer things like performance tuning, etc. You can always go to our streaming programming guide to get all those details. And obviously, you can ask questions. I'll be around. So, yes, one question. JMS connector, no, there isn't a JMS connector, JMS receiver yet, but I have heard people that they have written it. I just don't have the source code, but people have written it. Yeah. Yeah, okay, we're running out of time, so we can, let's have all the questions offline. You'll find me around, so just ask me.
All right, so we're going to keep on moving here. We actually have to make a little adjustment to the schedule. We had hoped to start all the exercises immediately after lunch, but we're going to move the GraphX talk to after lunch. So as soon as Amit's done with this talk, lunch should be available, and then you guys can go eat, and then we'll move on. Starting at about 1, we'll get into the next talk. All right.
Hey guys, all right, so I'm between you and lunch, so I'll try to be fast. I'll be talking about MLlib today. It's Spark's machine learning library. And my background's in large-scale machine learning, so with that lens in mind, I'd like to first motivate why we embarked on MLlib in the first place a few years ago, especially given that there are several other many open source libraries and some not that do machine learning and do it quite well. So when we were thinking about large-scale machine learning, there were a few criteria that we wanted to achieve. The first being, of course, scalability and performance. We wanted a library that worked on large-scale data, that took advantage of distributed cluster environments. Beyond that, we wanted a library that worked well, or that afforded a simple development environment, both to run algorithms, deploy them, and also to adapt given algorithms or write new algorithms within the library. And finally, we wanted a library that integrated well with other data processing components. Of course, machine learning is very important, but there's other things you need to do to get a pipeline running. So with these 3 criteria in mind, when we started looking around, we didn't really see anything that naturally fit the bill, so we embarked on MLlib. And I would argue that MLlib satisfies all 3 of these constraints. It's scalable and fast. Being part of Spark, it has a nice development environment. And again, as you've heard several times by now, the fact that it's part of this nice ecosystem means that you can do many different things along with machine learning, such as Spark SQL, streaming, GraphX, and so on. All right, so that's a very high-level overview, but for the remainder of the talk, I'd first like to dive into a little bit more about what is MLlib, what you can do there, and then I'll go into a few examples of how you can actually use it, and finally, I'll talk about a roadmap of what we expect to see in the next release and beyond. All right, so MLlib is an offshoot of MLBase. MLBase is an open-source project coming from the AMP lab at UC Berkeley. The idea of MLBase is to simplify the development and deployment of large-scale machine learning pipelines. It's a project that's built upon Spark, and the 2 goals are really higher order machine learning problems. The first is namely coming up with an experimental API that simplifies the development of machine learning. So instead of a machine learning developer having to implement things in terms of just bare bones map reduce, for instance, we want to expose higher level primitives, tables, matrices, and underlying convex optimization primitives to make development easier. On top of that, we wanted optimizers to auto-tune machine learning pipelines. So there's a lot of different algorithms for classification, regression, different other types of machine learning problems. There's also various feature extractors that you can use to process your data along the way. And each of these different feature extractors and algorithms have a lot of different parameters, hyperparameters that you need to tune. So the idea of this top level is to try to put these all together, search over this large space, and get a reasonable result. So these are the two high-level goals of MLBase, but in order to actually build them, we first needed a core within Spark that actually performed machine learning so that we could build on top of it. So MLlib naturally came out as a product of our higher-level goals in MLBase. And I get asked this question a lot about what the difference is between MLlib and MLI in particular, and so I just want to be very clear that it's, MLlib is a production quality machine learning library shipped as part of Spark, whereas MLI as well as MLOpt are experimental test beds. So the idea there is that we're looking at new, interesting research, hopefully interesting research questions, and successful ideas that we study in MLopt and MLI will percolate into MLlib once they're more mature. And we've already started to see that, and I'll point that out a little bit more throughout this talk. And also, I should note that Evan Sparks gave a nice talk yesterday at the Spark Summit about MLBase. So you should watch that video online once it becomes available if you're interested in learning more about MLBase. Okay, so as I mentioned, MLlib came out of, was an offshoot, the first release was an offshoot of the MLBase project, developed predominantly by the AMP Lab with a small number of contributors, shipped last fall as part of the Spark 0.8 release. But it's been really incredible to see the rapid development of it just in the last 9 months. So fast forward 9 months, we have more than quadruple the number of contributors. The latest release was included in Spark version 1.0 with a lot more of additional functionality. So for instance, if you just think about algorithms, in the first version, we had the algorithms listed on the slide. I'm not going to list each one of them, but basically we had common algorithms for classification, regression, collaborative filtering, clustering, as well as one particular underlying optimization primitive that was powering a lot of the classification and regression algorithms. Fast forward to version 1.0, we've added additional functionality for these 5 existing classes of algorithms. We've also added a new class of algorithms related to dimensionality reduction. And I'd like to point out one of them in particular, which are decision trees. And when we started talking about MLlib, even last fall, the thing that we kept getting asked about was decision trees and ensembles of decision trees. These are very popular in practice. They're interpretable. They support categorical variables and missing data. And as you guys probably know, ensembles of these, random forests or boosting, are top performers in practice. They're also very robust and kind of easy to use. So people really wanted these. We don't yet have ensembles in MLlib, but we have the decision trees themselves there. They scale very nicely. They work for classification and regression. And adding ensembles on top of them is kind of a thin wrapper given these decision trees. And so we also have to come up with some pretty neat optimization tricks to get these things to scale nicely in Spark. Manish Amde gave a talk on Monday describing this in more detail, so I encourage you guys to watch his talk if you're interested. Okay, so that's just in terms of algorithms, how we've, what was there, what is there now, but there's other new developments in the most recent release of MLlib. First, related to documentation. So we have a new, an updated user guide. We have some code examples and templates that help you navigate through MLlib. We also, as with the rest of Spark, we have API stability at this point. And finally, we've borrowed some ideas, as I mentioned, from MLBase, MLI already. One is sparse data support. The second is making matrices first-class objects in MLlib. So I'd like to talk about a few of these in a little bit more detail. So the first is the improved user guide. And basically, just the user guide is much more in-depth, more explanations, more examples. It's organized much better. We have code snippets embedded in the user guide to sort of give you additional information about what's going on with MLlib and how to use it. We've also included code examples which illustrate how you can actually use this on real-ish world data. And it's also, we've found that they've been useful as templates for standalone applications. So here's an example of a code example for collaborative filtering for the ALS algorithm included in MLlib. And basically, you can, working with a common open source or publicly available data set, you can run MLlib, and you can run MLlib or the collaborative filtering algorithm in MLlib and train a recommendation system. And I'll get back to this a little bit more later because for your exercises today, the MLlib component of it, you'll actually be doing something quite similar to this. All right, so we have examples not just for collaborative filtering, but also for various classification algorithms, clustering, regression, and so on. All right, another really important aspect of the new release of MLlib is the ability to exploit sparsity. So data is, in machine learning, sparse features are super common. I just listed here 4 examples of it, but you could list another 40. So text processing is very common. You represent text with bags of words or n-grams. In collaborative filtering, the main object here is a sparse ratings matrix. Various graphs or various matrices associated with graphs, including an adjacency matrix, are typically sparse. In genomics, the objects that you want to typically analyze, again, are sparse. So, I just pushed the wrong button. Sorry. Okay. Yeah, so MLlib is now supporting sparse storage and communication for certain classes of algorithms right now. So for classification, k-means, and summary statistics. And we've seen that this, not surprisingly, can have a big impact on performance. So here's one example of exploiting sparsity in the context of clustering with the k-means algorithm. And basically, we have this training set. It's Twitter tweets, 12 million examples, 500 features. Because it's text, it's unsurprisingly sparse. And basically, what we see is a 7x savings in storage, or 40 gigabyte savings in storage, and a 4x speed up in computation by taking account of sparsity. And I would argue here, actually, that this is actually not very sparse for a sparse data set. So typically, you often see data sets that are 1% sparse or less. So you could hopefully get even better results. And I would point you to Xian-Ri's talk on the first day of the Spark Summit, where he spoke in more detail about adding sparsity to MLlib, if you'd like to learn more about it. Okay, so that's kind of a rough overview of where we are today with MLlib. I'd next like to talk about, just to show you some examples of how you can actually use it. And these examples are going to be focused on k-means and collaborative filtering. So before showing the examples, I'm going to give a very, very quick tutorial on how each of these algorithms work, just to make sure we're all on the same page. So the first is k-means. And I hope many of you probably know this already, but the idea of k-means, it's a clustering algorithm where you want to partition your points into k clusters. So here's a toy example. You have 11 points that are roughly, as you can see visually, they're two-dimensional points. You can see that they're roughly are 3 clusters. So let's pick k equals 3. And then the idea of k-means is very simple. You just alternate between 2 different steps. The first step is to compute cluster centers. And here, one way, the naive way to pick cluster centers when you start is to just randomly choose them. So we're going to randomly choose 3 cluster centers. Then the next step is to assign cluster membership given cluster centers. So we have these 3 cluster centers, and basically for each point, we want to see which cluster center it's closest to and assign it to that cluster center. All right, so we do that, and now we want to go back to computing cluster centers again. So now we have these points that are colored. We know each cluster is represented by the subset of points that are within it, and basically we can recompute a cluster center just by taking the average of all the points within the cluster. So now we have new cluster centers, and again we repeat by assigning cluster membership, and you can keep doing this until you run it for a max number of iterations, or until it converges to some minimum. All right, so that's how k-means works. It's a commonly used algorithm in practice for exploring your data, or as a pre-processing step, for instance, for some sort of hierarchical modeling. You might want to learn a different classifier, for instance, for different clusters of your data. And how can we actually do k-means in MLlib? Well, these code snippets are really just meant to illustrate that it's pretty easy to do this. So in this particular example, we're loading a text file that's space separated. So the first 2 lines, we're just processing this text file. We then train a model with k-means by feeding it that data along with 2 parameters, the value k and the number of iterations we want to run. And then the bottom few lines, we're simply using this model to compute the error on the training data. So that's an example in Scala. You can do something very similar here in Python. And the one thing I would like to point out here is that, so here when training the k-means model, we're explicitly specifying the way we want to initialize the cluster centers. And I kind of glossed over that when going through the example, but randomly picking the cluster centers to start isn't always a good idea. Your results can vary a fair bit. There has been some theoretical results in the last 5-10 years showing that by being a little bit more careful about how you initialize, you can do much better. The default way in MLlib to pick cluster centers is exactly using this more sophisticated way of initialization, and here we're explicitly telling the algorithm to initialize it this way. And it's called k-means ++, or there's a parallel implementations of it, which is called k-means parallel, which is what you're seeing here. All right, so here's another example of using k-means. Here we're using it first by doing dimensionality reduction and then running k-means. I haven't talked about dimensionality reduction, but on a very high level, the idea is that imagine you have many observations and they're each represented by lots of features. Having lots of features, having a high dimension can be costly when you want to compute distances or just operate on this data. It also can lead you to suffer from what's called the curse of dimensionality, where in very high dimensional spaces, Euclidean distances are sort of not as meaningful as you would like. So both for computational reasons and potentially for statistical reasons, it can be a good thing to do dimensionality reduction before running k-means. So what we're showing here is an example of loading an RDD from some unspecified source, storing it as a row matrix in MLlib, running PCA on it to compute its top 20 principal components, and then projecting your input data onto these top 20 principal components to get a low-dimensional representation of your data. And now instead of running k-means on your original data, you're just running k-means on this low-dimensional representation of your data for computational and possibly statistical reasons. All right, so here's yet another example, and this is, sure. So you can use that model and feed it to new points to give you predictions. That's right. Partitioning and everything. I mean, models are typically, if K is very big, they can, so yeah. For certain sorts of models, you have to worry about that. But in this case, typically for k-means, your model's not going to be that big. It's just not an issue. Okay, so here's an example with streaming. And so Michael, when talking about Spark SQL, showed an example of Spark SQL with MLlib. TD showed also an example of streaming and Spark SQL. And I would argue that it's a really cool thing in MLlib that we have the opportunity to combine it with other really important components in a data processing pipeline. Here's an example that's very much similar to Ali's demo from the first day. And it's kind of just a toy example, but the idea is that imagine you want to process tweets in a streaming fashion, and you want to filter them based on some criteria. Imagine that criteria is that you only want to keep, as in the demo, tweets related to soccer and not those related to other sports. So you could do that by first training a model offline with some other data, and possibly doing the model you could train could possibly be a clustering model where you cluster your data, find the cluster associated with soccer, and then as you're processing tweets, you can run that model on each tweet, see if it's in the appropriate cluster, and only display it if that's the case. So this is sort of a toy example, but. Yeah, so that's a different thing, and that TD mentioned we want one extension of MLlib, which I think is really important, is adding online training of algorithms, or even if you do an offline training of an algorithm, how do you do incremental updates? We don't have that yet. There's it's an interesting research question. It's interesting in practice, but that's not covered here. It's a good question. So again, I would encourage you to look at Aaron Davidson's talk from the Hadoop Summit last month, or Ali's demo from a few days ago to see further examples related to this. Okay, so that's enough about k-means. I'll next talk about collaborative filtering, and again, this is what you guys will be doing in your exercises today. So just to remind everyone, collaborative filtering is typically motivated by this movie recommendation example. The idea is that you have movies and you have users. Some users have rated some movies, and what you want to do is predict the missing rating. So recover a matrix from a subset of its entries. At least in the research community, the Netflix prize 7 to 10 years ago really got people really excited about this, but of course lots of organizations at this point are very excited about this. Just mathematically, without making additional assumptions, this is just an ill-posed problem. If every entry of your matrix is completely independent, there's no way you can hope to learn from what you've seen. So you have to do something to reduce the degrees of freedom. And you do that by you can do that, and people often do this by making a so-called low-rank assumption. So the idea is that you assume that there's a small number of preferences that determine user preference and that describe movies, and doing so, you can drastically reduce the degrees of freedom in your model. So when you make this low-rank assumption, you have a linear set of degrees of freedom. You can actually hope to learn given a subset of the data. Also, it allows you to have a model that's a lot smaller. So that's going back to one of the earlier questions today. All right, so you make this low-rank assumption. There's many ways to now try to learn this model. What we currently have in MLlib is the alternating least squares algorithm. And this is a commonly used algorithm in practice, and it scales pretty nicely. And its flavor is kind of similar to k-means, as I talked about before, in that you alternate between two different steps. So I'll describe really quickly how it works. What I'm showing in this picture here on the left is this ratings matrix This is the matrix where you want to impute the missing entries. I'm denoting by the blue squares here the entries or the ratings that you have seen. So those are the observed entries. And the right-hand side are the user and the movie factors. So now if we look at the first row of this ratings matrix, we see the ratings that the first user has actually given to us. And we can describe the training error of this first user as the difference between each of these ratings and what a model would predict for it. So that's kind of what this pictorial equation in the middle of the screen is showing you. There's two terms. Each term is a difference between a rating and the corresponding prediction that a model would give you. That's just a dot product between two vectors, the user vector and the associated, the user features and the associated movie features. And the idea of ALS is basically that we want to alternate between updating the user and movie factors. So going back to this training error, there are two unknowns here. So the blue box, the ratings are fixed, they're given to us, but we want to learn both the green and the orange feature vectors, but we don't want to learn them both at the same time. Instead, we fix one and try to learn the other. So if we want to update the first user, for instance, we would fix the green feature vectors and just try to find the best orange feature vector to minimize the training error. This can be reduced to a standard linear regression problem. Moreover, you can do this in parallel for all users at the same time. You have to be a little bit careful about how you minimize communication for large-scale problems. But if you do this in a reasonable way, you can do these all in parallel. Once you're done with all the users, you can then go back and do the same thing for all the movies. And again, keep doing this in an iterative fashion until you converge to a stable answer, or until you run for a certain number of iterations. All right, so that's ALS. And this is an example of how you actually would run ALS in MLlib. And again, it's pretty simple. You're first loading some data and parsing it. You want to create a ratings RDD, which stores tuples of user, item, and ratings. You then train an ALS model by feeding it into this ratings RDD, and also hyperparameters of the ALS algorithm, the rank, the regularizer, and the number of iterations you want to run. And finally, you can use the learned model to make predictions on new data, or in this case, on the training data in the first place. All right, so that's a simple example. And what you guys will be doing in your exercise today is extending that. So basically, you'll be working with this movie lens data set. There's two versions of this data set, a smaller and a bigger one with 1 million or 10 million ratings. What you're then going to do is you're going to be asked to rate some examples yourself of the movies that are included in this data set. Given this training data, or given this labeled data, you're going to split it into training and validation data. You're then going to fit a model using the training data, either in Python or in Scala. You're then going to see how well it performs by seeing how well it performs on the validation data, so computing some sort of validation error, and then try to improve that model by tuning different parameters to see how high you can get the validation error. And finally, once you get a model with sufficiently good parameters, you're going to get recommended. You're going to run that model to see what it recommends to you. The movies in this data set are kind of old, so don't be too excited about the ratings, but I think it's a pretty cool example of how you can do this pretty quickly in MLlib and Spark. Okay, so that's some examples. I'd next like to briefly conclude by talking about the roadmap for MLlib moving forward. So as you may have heard by now, Spark is on a 3-month release cycle. So the next release, the cutoff for features, is the end of July. And so what do we have planned for this next release? Well, the first is that we want to further standardize interfaces within MLlib. This is, again, borrowing from ideas in MLI. And in particular, one thing we want to work on is for different there's many different underlying optimization primitives that you can use to train a particular model. So there's different ways to learn an SVM classifier, or logistic regression, or so on. And we want to have different ways. We want to have abstractions that are separating the underlying optimization primitive versus the model that we're trying to learn. And this is an idea from MLI. Second, we're hoping to get parallel model training into MLlib. It might not happen for this release. If not, it'll happen in the next release. But the idea here is that you often have to train multiple models at the same time because you want to learn optimal hyperparameters for them. And as Evan talked about in his talk yesterday, you can often do this. If you train things in parallel, you can kind of often do that for free, given that it takes longer to read from memory than it does to do computations. Next, we're adding a statistical toolbox for descriptive statistics, sampling, and hypothesis testing. We're also adding additional learning algorithms and additional optimization algorithms. And then beyond version 1.1, what do we expect? Well, It's hard to know exactly. It's kind of depending on the community a fair bit. But one thing I think it's safe to say is that we're hoping to have scalable implementations of standard machine learning algorithms and optimization primitives. I think we've already seen rapid growth in the last 9 months, and I think we're well along the way of covering many of the important algorithms that people care about for machine learning. So second, we want to continually improve the documentation and have consistent APIs, and we've already started doing that. And furthermore, we want to support machine learning pipeline development. So part of this is related to the ML-based project in terms of auto-tuning, but we also want to add common feature extractors for typical sorts of problems related to images or text, for instance. We also want to add additional code examples and templates that people can use, hopefully to maybe build their own applications. But of course, these are just ideas. Feedback and contributions are encouraged, and the interests of the community are really is what's going to guide future functionality into MLlib. So please contribute and discuss if you're interested in adding things. And so with that, I will conclude, let you eat lunch. If you are interested in learning more about MLlib, you can check out the user guide. And I'd like to thank all the many contributors to MLlib. And that's it. Thanks a lot. So it's a stretch goal to have ensembles of decision trees in 1.1, but it kind of depends. So hopefully 1.1, but I would not want to commit to that. But I would say that random forest and boosting are two of the things we hear most about that people want. So it is very high on our priority list. We just want to make sure it's working well and thoroughly tested before it's added. All right, great. Well, I'll be here all day, so happy to answer more questions throughout the day. Thanks again. Sorry. Just wanted to let you know that food is ready, so enjoy lunch.